Yo, what's up everyone? My name's Dave and you suck at programming. Alright, to get started, we're going to jump into some Bash right here, alright? Here's your cringe script. This is what you think is good. Look, we have a Bash script here, as you can see it executes bin bash. Then we do for f in ls files, and then we echo file is $f. Well, that's ls files. We'll see what's in there. Bam, okay, we got 5 files, A, B, C, D, E. If we run this little cringe script, look at that. We get 5 lines, 5 files. It makes perfect sense. However, let's slow down. Let's look at this base script, alright? Your cringe script sucks. Let's look at this base script. All right, user bin env bash. Look at that. We're not hard coding bin bash. We don't know where bash lives on the user's machine, so we're just putting this line in. This is way better, way more based. All right, for f in /file/star. Look at that. We're using a glob operator that's built into bash. We're not executing an external program like ls. This is better. Look at this. We're even quoting the variables. Echo quote file is $f quote. We didn't forget our quotes this time. Let's run this base script and take a look. Uh-oh, what do we have here? We only have 4 lines. Isn't that kind of weird? Files A, files B, files C, files D, space, E. Wait, what the hell's going on here? Let's do a long listing on files. Uh-oh, looks like we only have 4 files. I tricked you. There's only 4 files. One has a bunch of spaces in it. Your cringe script didn't detect that, but this base script did. This is how to write better bash. Hey, what's up everyone? My name's Dave and you suck at programming. All right, let's jump right in. We're talking about arguments in bash today, okay? How to loop over arguments in bash, how to process them. Let's take a look at your cringe script. Here's what you think is right. What you want to do when you loop arguments in bash, you want to say for arg in $, and then you want to print out the arg. Look at this, you have it quoted. That's good. You're using a little less than and greater than. Not necessary. You're just doing that for style points. Awesome, fine. But there's something wrong with this. I'm going to show you what it is. All right, let's look at your cringe script. Let's run a foo bar baz. We run it. Okay, cool. We got 3 arguments. Foo bar baz. That makes sense. What if we didn't have 3 arguments? What if we had 2 arguments? Nah, you still think we have 3. What if we had 3 arguments, but a bunch of spaces in one? Look at that. You think we have 5 arguments. That's insane. Your script sucks. Let's show you how to make it better. All right, let's take a look at this cringe script. We're going to do it live. We have a $* here. That's not right. So what do we do when we don't know if something's right in bash? We quote it because we don't really know what we're doing. So let's throw quotes around it. What's going to happen when we do this? Well, we'll run it again. It didn't work. Okay, now your program thinks we have 1 argument. That's even worse. 1 big argument constructed from all the arrays. Terrible, terrible. Let's get rid of these quotes. Clearly that didn't work. The star is probably the problem here, right? Let's change it with an @ We've seen that before. Maybe this will help it. Run it and we got the same problem. It looks like an @ and a star are the same when you don't use quotes, because they are. That's a hint. I'm giving you that. That's giving you that for free. That's your hint. Let's put quotes around this and see what we get. Quote $@ quote. Run it and bam, look at this. This is amazing. We gave in 3 arguments and we get 3 arguments back. Foo, bar baz, hello, space, world. We get the arguments we want. Let's take a look. If we diff our cringe script to our base script, there's no differences because we have made our cringe script base. There you go. That's how to handle positional parameters in bash. Yo, what's up? My name's Dave and you suck at programming. All right, today we're going to talk about listing files in bash. Again, we talked about this in part 1, but a lot of you had stuff to say in the comments that was just plain wrong. So I'm going to talk about why your scripts are cringe and why mine are base. All right, get started. We're going to see what you guys said. In the comments, a lot of you said I could do ls and I could pipe that to a while read line. This might work, this may not work. In order to talk about this, we have to talk about how this works. So when you ls something, like if I ls the current directory, its output changes if I'm outputting to a terminal or not. If I'm outputting to a terminal, it's all on 1 line. If I'm not outputting to terminal, you can see it's separated by new lines. So we're taking advantage of this. We're LSing files, separating them by new lines, and piping them to a while read line. So if we run your still cringe script, you can see, looking at the data we had from the first set, A, B, C, D, space, A, space, E, hey, that looks pretty good, right? Let me ls files and make sure. Uh-oh, what's going on here? What happened to file B? Why is it all messed up like that? Let me do a long listing on files. Okay, I can see a file named A, B, and then what is going on here? Let's figure this out. Well, let's ls files and pipe to cat like we did before. So if we do this, we can see that, looks like there's 4 files here, right? So what is happening? Well, let's look at my base script. The base script is going to use the bash built-in glob operator. We're going to loop over it in a for loop. Run the base script and bam, we can see that there are actually 3 files. Files B, new line C. That is 1 file with a new line character in it. The base script that I show you in part 1 can actually handle this. The ls script you guys told me about doesn't handle this. Okay, so what you guys thought was base was actually cringe, and what I showed you was base was actually base. All right, they hated Jesus too because he told the truth. So yeah, this is how to loop files properly in bash. Yo, what's up everyone? My name's Dave and you suck at programming. All right, today we're back in bash. All right, a lot of you had stuff to say on my first couple of parts talking about for loops. You were saying I could use a find command and pipe it to a while loop instead of using the for command. So let's take a look at this. All right, so we have files again, and what kind of files do we have here? You know there's gonna be question marks. You know there's weird stuff going on. It's me, so you know there's gonna be some trickery here. Let's do a long listing on it. We can see that there are 3 files, one named A, one named B, space, C, and one named D, some character E. What do you think that some character is? Let's find out. A lot of you are saying we could use a find command, so let's do that. Find the name of the directory, which is files, and then type F, meaning we're only looking for regular files. When we do this, we can see that there are 3 files. This one has a new line in it. So even though there's 3 files, there are 4 lines. Remember that, that's important. So let's pipe this to a while loop like a bunch of you said we could do. While read file, do echo, and then we'll put some greater than less than signs around it just to make it easy to see. And if we print this, we can see that, we have 4 entries here, even though we have 3 files. See, the new line's a problem. Because we're using a new line as a delimiter character, and also the file has a new line in it, that's a problem. That's why your script sucks, right? So I'm gonna show you how to make it better. Instead of using new lines to delimit it, we can use null bytes. Now, some of you said this in the comments, so I guess some of you are kind of based, but still a little cringe, and I'm gonna show you why. So let's do this. Print 0. This means we're gonna separate the files by null bytes. And in the read command, so right here, this is a read built in, we're going to do -r for raw, or we're going to do -d for delimiter. The delimiter is an empty string. Why? Because an empty string ends in a null byte. We're telling it to delimit based on null bytes. So if we run this now, let's take a look. Look at this. We only have 3 things. 1 file, 2 files, 3 files. That's what we want to see. That's correct. Isn't that awesome? Look, it's almost base, because this is what you guys suggested. However, it might still be cringe. Let's find out. Let's take a look at this script. So it's hard to read when it's actually on the command line like this. So let's put in a script. We got a cringe script here. Let's open this up. All right, this is exactly what I ran before. We're gonna find files, print 0, while read line, cool, echo file, awesome. What if we wanted to count them? I equals 0. We'll do a nice I++, and then we'll echo found $i files. So this should loop 3 times. We should increment I to 3, and we should say found 3 files, right? Let's run this cringe script. All right, we found 1 file, we found 2 files, we found 3 files, and found 0 files. What the hell is going on? Isn't that super weird? I thought we were incrementing. Right, what's going on? Well, all of you guys that suggested this, you're still cringe. You know why you're still cringe? Because of this right here. This pipe, everything over here gets executed in a subshell. So I gets copied into this subshell, and it does increment. But when this subshell is over, it's gone. That memory is gone. I is still 0. I here is the same as it was up here. None of these modifications actually affected the current running shell. So how do we fix this? Well, let's take a look at the base script. Can you guys guess what the base script is going to look like? That's right, it's going to be a for loop like from part 1, because what I'm telling you is the way to do it. Just use this, you won't run into any weird problems. You can actually count the number of files in a directory without having to worry about it. We run it, bam, found 3 files. There you go. That's how to loop files, still using a for loop and not a find command in Bash. Yo, what's up everyone? My name's Dave and you suck at programming. Alright, before we jump in on this one, I need to talk to you guys real quick because you're being really cringe in the comments. It's called You Suck at Programming, but I seem to cover Bash a lot, and a lot of you guys are saying, why? Why do you call it programming? It's Bash. Don't you know Bash is scripting? Scripting's not programming. They're totally different things. Well, that's great for me because you guys in the comments just keep commenting that. You know what that does? That boosts me in the algorithm. So go ahead. If you get angry at me, if you get upset with me, put it right in the comments. Just bring on the hate. Boost these videos in the algorithm. You are helping me out. All right, let's jump in on this one, okay? We're going to switch gears a little bit. We're still in Bash to make you guys happy. I know you guys love Bash so much. But in this one, we have a text file with some data in it. Now let's look at this data real quick. Okay, you can see the data is colon separated. We have 3 fields, name, an ID, and a description. So you can see Dave is a cool guy. His ID is 56. James 1 is also a cool guy. He has an ID of 23. James 2 has an ID of 22. And his description is James 2, a cringe loser. Well, look at these descriptions, though. There's actually a colon in the description, even though we use colons to separate the fields. Is this going to be a problem? Let's find out. So first things first, we're going to look at your cringe script. Here's how you would parse that data. So you have a cringe script that looks like this. We do a while read line, and we read in from data.txt. Actually, that looks fine to me. We extract the name, the ID, and the description. The way we extract the name is we echo the line, and then we pipe it to cut on colons, grab field 1. Okay, that'll work. ID, cut, and colons, grab field 2. That also works. For description, cut on colons, grab field 3 with a hyphen at the end, meaning field 3 and anything beyond it. This'll actually work. And then you print ID colon name is description. So if we run your cringe script, 56, Dave's a cool guy, 23, James is James 1, also cool. This works. Maybe you guys aren't as cringe as I thought you were because the script you are showing me actually works. But it's still cringe, and I'm going to show you why it's cringe. All right, you guys ready for this? Let's talk about it. What's happening here? Well, we're piping to cut. Every time we loop a line in the text file, we actually fork an external command. The external command is cut. For every line in the text file, we have 3 forked commands here. So because we have 3 lines, 3 times 3, we are forking 9 times in this script. Can we get that number down? Let's find out. Let's look at the base script that I have. Get ready. It's a lot simpler. Bam. Here it is. what we do is we do a while read line the same way we did before. However, notice there's something unique here. We have the inner field separator here. We're setting that to colon. And then we're reading the name, the ID, and the description right in this while read line loop. Cool. What does that do? Well, it defines those variables and breaks them on colons, and anything beyond the third colon gets stored in the desc variable short for description. So echo ID name is description. When we run the base script, what do we get? We get exactly what we think we should get. We get exactly what the cringe script gives us. The only difference is the base script doesn't fork and exec any external commands. All the string manipulation is done in pure bash alone. So even though the scripts output the same things, there are ways to clean up your code to make it simpler, easier to read, and fork less external commands. And that is how to do basic string manipulation in bash. Yo, what's up? My name's Dave and you suck at programming. Alright, to get started, we're going to talk about the thing I talked about last episode in part 5, my based and cringe script for parsing data in bash. So as you can see, we have this data that we want to parse and it's separated by colons, and we have the based way and the cringe way. The reason I'm making this episode is because some of you had questions on how do I know what's actually going to fork and exec external commands, because you guys are cringe, and I'm going to show you how to do it in a based way, alright? So first things first, I'm not on Linux like some of you guys assume, and on this example, I'm not even on my Mac system. I am on an Illumos-based system, so I have DTrace, and that's how I'm going to answer this question. So first things first, let's look at the cringe script. The cringe script is a while read line, but the most important thing is here. We fork the external command cut, and cut. We do that 3 times every time it loops, and how many times we loop? Well, that depends on how much data we have. In this example, we have 3 lines of data, so 3 times 3, we're going to fork 9 external commands here. As opposed to the base script doesn't actually fork any external commands at all because echo is built into the shell. You can verify that with type, and you can see that echo is a shell built in, whereas cut is user bin cut. That's an external command. So how do we do this? Well, we're going to need to fire up some DTrace. This is going to be a lot. If you've never seen DTrace before, oh boy, buckle up, this is going to be fun. But what we want is we want to trace proc exec success. This is every time an exec syscall is successful. And then we only want to look at the progeny of the $target. If this is a lot, yeah, just try to keep up. Fine, don't worry about it. And then we're going to trace cur ps info, which is our current process information, and we want ps args from that. So this is the arguments of the command that got forked. And then what command gets run? Well, we can run the command right here. So let's run the cringe script, and let's see what it does. So bam, okay, we ran the cringe script ran, and as you can see, we forked our bash script here, fine, and then cut ran 3, 1, 2, 3, 1, 2, 3. Cut ran 9 times, exactly like I said. Field 1, 2, 3, field 1, 2, 3, field 1, 2, 3. So we forked an exact 3 instances of cut per loop, so 9 times. As opposed to if we run that against our base script, we can see that the only thing that got forked and exec here was bash itself. There was no external commands. And this is how you track external command forking in bash with DTrace, so I kind of cheated. Yo, what's up everyone? My name's Dave and you suck at programming. Alright, we're gonna jump right in. A bunch of you guys are being big crybaby losers in my comments. You guys are being super cringe, basically saying, does this guy even know what he's talking about? Does he just iterate through things? Does he just do a bunch of guesswork? It looks like he doesn't even know what he's talking about. I do that for your sake. Of course I know what I'm talking about. I know everything. I'm literally the smartest person that's ever lived. Okay, so when it comes to bash and you guys are wondering, oh, how'd you know to do this? You're just doing a bunch of guesswork. No. I read the documentation. It's super easy. You guys ready for this? I'm going to show you how you do it. You can do this at home. You can follow along. Ready? Man, bash. There you go. Documentation for bash. Alright, jokes aside, I'm being 100% serious. Read through this. If you really want to understand the shell that you use on a daily basis for your job, if you're like a developer or you're just interested in tech in general, 1000%, not joking, no sarcasm, read through this. Take the time, read through all of this. You will have such a better understanding of the shell. It will no longer involve a lot of guesswork. You'll understand when to quote certain things, when to use curly braces. Things will just make more sense. There are so many good sections in here. It shows you what a login shell is. It shows you which files are read when bash starts, whether that be your bash profile, your bash login, your profile, your bash RC. There is so much good information in here. And, oh, man's not happy with me. All right, so let's back out real quick. So what can we do? Well, in the shell, if you want to know if something is built into bash or an external command, I talked about this in previous episodes, you can use the type command. So if I run type echo, I can see that echo is a shell built in. Now, some of you would say, well, I can just use the which command. Which tells you where it is on your file system. So for the which command, it sees bin echo. If I do man echo, this brings up the man page for that command. As you can see, echo doesn't support a -e. So if I were to call /bin echo -e hello world, it would actually print -e hello world. That's not what I expect, because if I call echo just as a bash built in, it interprets that argument and doesn't print it. As you can see, there's a difference there. And the reason for that is if you use type -a, I can see that echo is two things. It's a shell built in and it is bin echo. So the shell actually prefers the shell built in over what's on the file system. So use the type command, and if you want to get the man page for that built in, you can use the help command. Run help on its own and you can see every built in that bash has. If I run help echo, I can see here's the documentation for echo. As you can see, there's -e like we expected, even though the one in the file system did not support it. So use the help command. That's super base, definitely not cringe. Use the help command in bash to understand more about the built-ins. Read the man page. You will understand so much more, and that's how to get better at bash. Yo, what's up everyone? My name's Dave and you suck at programming. Alright, today we're going to demystify running programs in bash. You might be thinking, running programs in bash? That's super simple. I type the program name and I hit enter. Well, let's get into how complicated it can be. Alright, to start off, let's run echo -e hello world. Really simple. We can see that it prints hello world. The -e was written or was read by the built-in echo. How do I know it's a built-in? Well, I can run type on echo and see that's a built-in. There's also an external command, echo, where I can use I can run which to see it. So if I were to rerun that same command with bin echo, you would see that it didn't interpret the -e. That's because bin echo is different than the bash built-in. When in doubt, run type -a, and you can see every possible thing. Bash will start at the top and work its way down, so it'll prefer the shell built-in before the command. That's very simple. I'm just reiterating what I went over in last episode. Let's complicate things. Well, the first way to complicate things is when I'm running interactively, I can make an alias. I can make an alias called echo, and I can set that to echo foo. So now every time I run echo, like echo hello world, you'll see that foo shows up in front of it. That's because it's replacing echo with echo foo. If I were to run echo -e hello world, you can see the -e is no longer being interpreted by echo. That's because it's coming after foo. It's not being interpreted as an argument. So that throws a little wrench in the problem. Let's make it even more complicated. You ready? This is going to be a lot of fun. Let's make a function called echo, and let's have it call echo bar with all the original arguments. I'm not going to hit enter yet. The reason I'm not going to hit enter yet is because if I define this function, this is actually potentially very dangerous. This function calls itself. That's recursive. I will blow out the stack if I do this. It will just keep piling up. It will go into an infinite loop of trying to call itself. So in bash, if I want this to not call itself, I have to put the word command in front of it. Command is a built-in. You can run help command to find out more. Command will tell it to go through the normal processing. It will skip the functions. It'll skip the aliases. It will go right to the built-in if I run command. So there we go. Now I have a function. Now I have an alias. So what does that mean if we run type -a echo? Ooh, we got a lot going on here. The first thing we have is the alias. Aliases are preferred first. The next thing we have is the function. Functions are preferred next. The next thing we have is the shell built-in, and the next thing we have is the external command. So if I were to run echo -e hello world, what would happen? Well, it's really simple. We can just run it and find out. Okay, we got bar foo -e hello world. Why did that happen? You guys might be asking me. I'm going to show you why. I'm going to break down exactly how that happened. So first things first, we ran echo with -e hello world. That's the arguments we gave it. So what got ran first? Well, the first thing we run is the alias. The alias runs echo with foo as the first argument. So let's put foo right in front of it. That's the first thing that happened. The next thing that happened is we moved on to the function. So the alias called the function bar with all of the original arguments in front of it. So it put bar here, it ran all the original functions in front of it, and then because of command, it ran the shell built-in. So the shell built-in echo got ran with bar foo -e hello world. And we can verify this by running it manually ourselves. If we were to do command echo, we get the exact same thing. That's how it ran. The only difference is I have one big string. These got ran as separate arguments. But yeah, that's demystifying commands in bash. Yo, what's up everyone? My name's Dave and you suck at programming. All right, we're going to jump right in with some bash and we're going to demystify variables this time because a lot of you guys are confused when it comes to variables. Why would I use the export keyword? What does environmental mean versus my local variables? What's going on? This is confusing. All right, I'm going to show you cringe losers how to do this. All right, first things first, we're going to echo a variable called $all caps foo. And what are we going to get? We're going to get nothing because no variable is defined with that name. So let's define a variable. What if we set foo equal to hello world and then we were to echo it again? We get hello world. Hey, that makes perfect sense, right? Well, let's move on to a little script I have. I have a script called echo foo. There's no trickery in this script. It's a 2-line script. We just echo $foo. It's exactly what we're doing on the command line, but we're doing it in the context of the script. So let's run that script. /echo foo, and it's empty. Isn't that kind of weird? We just defined foo up here. Why would it be empty? Well, the reason it's empty is because we defined foo. That's for our local variable. When we run a script, we're running that in a new process that goes through a fork, exec, and none of those variables are copied over. Unless we export them. So let's export foo. What does this do? This takes whatever's in the variable foo and makes it available as an environmental variable. So now it's in our environment. Now when we fork an exec, that should be carried through, and we can verify this with echo foo. And we can do this all in one command if we want to. We could say foo equals hi Dave, and then we could run this and hey, it works. We could say foo equals you're cringe, And same deal, right? No surprise there. Cool. We can also temporarily override it. You may have seen this syntax before. Foo equals, let's call it temporary. And if we run it, you can see that foo is set to temporary, but if we just echo $foo, we actually didn't overwrite it. It's still your cringe, even though we temporarily set it when we executed a program. And hopefully this has demystified some variables in Bash for you. Yo, what's up everyone? My name's Dave and you suck at programming. All right, today we're going to talk about configuration files in Bash and how to parse them. All right, we're going to use our own format for a configuration file, and it's going to look something like this. It's going to look like key equals sign value. All right, so as you can see, we have foo equals 1, bar equals 2, baz equals 3, and then a whole bunch of crap to the right. Kind of interesting. Let's see what we can do. Well, we can take the naive approach. This is what you guys think is right, all right? I have a cringe version of this script that you guys wrote. You guys sent this in. You were like, hey, this will work, right? We can just source it, and then we can just print them out, right? Let's see. You think this will work? And we run it, and what happens? Uh-oh. It prints hacked, lol. Uh-oh. That's kind of weird. And we can see foo is set to 1, bar is equal to 2, and baz is equal to nothing. That's kind of weird. So what happened? Well, bash -x. We can run this with -x, which will give us trace debugging, and we can see the first thing it does is it sources conf, and then it sets foo equal to 1, bar equal to 2, baz equal to 3, and then it runs echo with baz set to 3. So we can see down here, foo is equal to 1, bar is equal to 2, baz is equal to nothing. So it actually ran this echo command. You can see the double plus sign means it's running inside the source file. It ran this echo command. That is not what we want. We do not want configuration files running commands. So how do we fix this? Well, let's look at my based way of doing it. This is a lot, but let's go over it line by line. The first thing we do, we need Bash version 4.0 for this to work. We define an associative array called conf. Then we loop the file line by line. We separate on the equal sign. We read the first thing, the left side of the equal sign, to key. The next thing, the right side, we set it to value. And then we set conf key equals value. Now we have an associated array with 3 keys, so we can just print them out. Conf foo, conf bar, and conf baz. So if we run the base script, what do we get? We get what we should get. We get foo is set to equal 1, bar is equal to 2, and baz is equal to 3, echo, all that crap to the right. The important thing, that echo command did not run. It is actually just set in the variable as a string. Bash didn't try to interpret it as a command. It just treated it as a string. We can verify this with bash -x. There's going to be a lot of output here, but as you can see, no echo command was actually run with hacked lol. The only thing that was run was echo with the whole entire thing as a string. That is how to safely parse this configuration file in Bash. Yo, what's up? My name's Dave and you suck at programming. All right, let's get started. Today we're talking about parsing file names in Bash. Okay, so what do we have? We have a directory called files, and inside that we have one file. As you can see, it's named Fun Family Party, then there's a hyphen, and then there is a date stamp here, and then there's an extension. It's a .jpeg. Cool. What do we want? Well, we want to parse it to look like want.txt. As you can see, we have the date here with a colon, and then the name to the right without the extension. So how are we going to do this? Well, here's the way you guys think is good. This is the cringe way of doing it. This is the wrong way of doing it. Here we go. Let's take a look. What do we do in Bash? Okay, we loop over the files. Cool. And for each file, first thing we do is we get the base name. Fine. This chops off the directory in front of it and just leaves us with the name of the file. Cool, fine. We get the name of it by echoing the base name into cutting it on hyphens and grabbing the first field. Fine. We get the date by cutting it on hyphens and grabbing the second field and everything thereafter. Okay, fine, that works, but we have to get rid of the extension. Okay, so we cut it on a period, and then we get rid of, we only keep the first thing to the left of the first period, fine, and then we pipe that to xargs echo. It's kind of a weird way of getting rid of the white space at the beginning and end of the line. And then we echo the date and the name. Well, does this work? It does work, but it's very brittle. It's exceptionally brittle. There is a better way of doing this. I'm going to show you how to do it, and it's really cool because Bash supports regex. We can use this. If you've never seen regex before, this is going to look way more complicated. You might want to go learn how that works. This is outside the scope of this video, but Bash can support this without any external tools. So what do? We loop the files. We say if the file name is equal to tilde, look at that, equal tilde right there. That's important. Equal to the regex that we have up here. That means that it matched, and there's a new variable created for us, bash rematch. This is regex match, and you can see that we grab the first field, which is the name, and the second field, which is the date. So the first field is what comes here, and the second field is what comes here all the way to those parentheses. And then if we run this, we can see that there were no external commands forked. It was just Bash doing regex matching on its own. So that is a base way of doing regex matching in Bash. Yo, what's up? My name's Dave and you suck at programming, except today you suck at using the command line. I'm gonna show you how to fix it, all right? Today we're gonna talk about timing commands in Bash, or how to time things on the command line. This is super easy. So let's say you're on the command line, you wanna run a command like echo hi. All it does is print hi back to you, right? Pretty fast, shouldn't take long. Well, did you know that you can run the time command in front of it? And what does this do? It runs your command and then it gives you timing statistics at the bottom. Real, user, user and sys. I won't go into details on what those are, but the real one is actually pretty much close to your clock time or how long it actually took. We can verify this. We can run something like sleep2 with the time command, and then after 2 seconds, you should see that it finished, and it took around 2 seconds. There's other things that happen on your computer, so it's not going to be perfect. That's a really simple way to time commands, but things might get a little hairy, and let's talk about how things can get hairy, all right? So let's say we want to time something that has sudo in it. So sudo runs something as, in this case, the root user. So when I execute, it's going to ask for my password. I'll type my password in, and you can see that it did what we expected. It printed hi, and it printed this, and the sudo command, all that did was run it as the super user. What if we had those arguments backwards? What if we called sudo time echo hi? What would happen? Well, look at that. Isn't that weird? The output's slightly different. Why is the output slightly different? Are we running as root? Well, we were running as root in the first one, so why would the output be different? Here's a really fun thing. You ready for this? Let's look at the type of sudo. Sudo is an external command. Let's look at the type of time. Time is a shell keyword. Time is built into the shell, sudo is not. So when we ran this command, sudo is an external command, it didn't run the time that was built into the shell. In fact, it didn't even run echo that was built into the shell. It ran both of those as commands. We can verify this by running type-a time and type-a, what was the other one? Echo. So you can see the first thing is these are shell built-ins or a shell keyword, but then there's external command variants. So when you call sudo, it runs the external command. We can verify this by running it ourselves. We could run user bin time, where is it? There we go. Bin echo hi. And we get the same output without having to run sudo, without having to escalate our privileges. So this is interesting. Make note of this. Sometimes commands you're running, they may be built into the shell or they may be external commands. And the order of operations you run them, like if you were to run sudo time or time sudo, can affect that. The easiest way to know is to run the type command, type-a, and see what happens. Also, let's expand on this a little bit. These commands can be slightly different. So let's talk about the time command. If I were to man time, I can see on my Mac system, I have a lot of arguments here. I have -a, -h, -l, -o. There's a whole bunch of stuff that time can do on a Mac. What if I run help time? There's only -p. Help is what's built into the shell. Man is for the external command. This is how to time things in Bash, and hopefully I demystified it a little bit for you. Yo, what's up? My name's Dave, and you suck at programming. All right, today we're going to talk about date parsing in Bash. Okay, date parsing, it's no one's favorite thing. This is a nightmare working with date and times, super annoying, especially time zones. But we're going to cover just the basics and the bare minimum here, just so you can understand what's going on, and you can feel kind of a little bit better when it comes to parsing the date in Bash. All right, first things first, you have a command, date. You run it, and it gets you the current date. Really simple. You can also give it a format string. So if you use a plus sign, you can say time is, whatever, hour, minute, second, and then the date command will replace that with the current hour, the current minute, the current second. If I run it again, you can see it's updated. This format is called strftime or strftime. You can learn more by using the man page here. It's a pretty standard format. You'll find that a lot of things use it. There's a lot of percent signs you can replace with different parts of the date. Super useful. But did you know that it's built into your shell if you're using Bash and you're on, like, I think it's Bash 4.0 or something newer? Either way, you can use printf. Printf has its own set of formatting, so I can say like, hello, %s, and then %s will get replaced with whatever string comes next. So if I put user, it'll say, hello, Dave. Cool, pretty nice. Well, with printf, I can also say time is %t for the time, put a new line, and then this won't quite work on its own because inside here, we can put parentheses, and now we can put formatting strings in here. So we could say, hour, minute, second. Cool, and we get time is. Now, there's a little bit more than that. We have to put a -1 here. We didn't have to in this example, but this can get more complicated. -1 tells Bash that we want to use the current time. There are other things you can use, like the date the shell started. You could also give it your own epoch time, and it will format that. But for this case, we're just going to use -1 here. All right, pretty nice. Speaking of the epoch time, let's say we want to go backwards. Let's say we want to express the time in some sort of way that we could parse later. Well, we can use the epoch time. This is the Unix timestamp, epoch timestamp, whatever you want to call it. This is the number of seconds that have elapsed since January 1st, 1970. If this is new to you, you're probably like, what the hell is wrong with computers? Yeah, I agree, but it's super useful. It makes parsing dates super easy. So date plus %s, this is a pretty common way you'll see of doing it. It's also built into printf. So again, if you have the T notation, the %T notation, you can put a %s, just like we used above. And, don't forget the new line, because it's printf. And we get the same thing, only this time it's built into the shell and it's not forking external date command. Even better than that, even newer versions of Bash have a special variable for us, epoch seconds. This, when expanded, will be the number of seconds that have elapsed since January 1st, 1970. We don't need printf, we don't need the date command, we can just do this. While we're here, we could also look at epoch real time. This is the exact same thing, but with microsecond resolution. Very useful. Pretty cool stuff. So yeah, there's some magic variables in Bash for parsing date, and hopefully this demystified parsing and using dates in Bash. Yo, what's up? My name's Dave, and you suck at programming. All right, today we are going to learn what this means. Now, you've probably seen this before. Okay, let's pull it up in the terminal just so we can see it and talk about it here. Bam. This is called a fork bomb. This is called a pipe bomb. This is a dangerous command. Do not run this command. However, we're going to break it down today. We're not going to run it, but we're going to break it down today and talk about how it works and why it's so dangerous. Because what is going on here? That's some wild syntax, isn't it? Well, okay, let's take a look. First thing we can do is we can unminify it. So this will make it a little bit easier to read. You know what, in fact, let's just edit this file. Bam! So this is what that looks like when we put enters in. We put new lines, we put spaces, we put white space, we put things that make it a lot easier to read and some syntax highlighting. So what do we have here? Well, this is still a little bit confusing. So instead of using the name colon for the function, let's change that out. Let's just call it myfunc. How's that? There we go. This is a lot simpler to read, okay? So what do? We define a function called myfunc, and what does that function do? It calls itself, and then it pipes that to itself, and then it forks it off in the background. And then right down here, this is the trigger. This is what triggers the initial call of the function. So let's think about this. What happens? We call our function calls itself twice, and then puts that in the background. So then those two functions will go off and call each other twice, and this one will call each other twice. So it's gonna get a little confusing, but let's look at the diagram I've laid out for you. So as you can see, function gets called first, and then it forks off two functions. Those fork off four functions. So as you can see, it's growing exponentially. We start with 1, then we'll get 2, 4, 8, 16, 32, 64, 128, 256, etc. It'll keep going. It's bad news. You will exhaust your system of resources. If you're in a newer system, like a Linux system with systemd or something, or you're on a Mac system with ulimit set fairly low, this will not be a problem. This will get caught. It's still annoying to deal with, and you'll bump up against these limits, but this is a potentially dangerous command. Still, do not run this. This will just exhaust your system of resources. It's not great, but it's still a cool thing to look at, and just like seeing the actual command itself, it's just really great. It's just awesome that someone could done something so small like that that's just so dangerous. So yeah, that's a fork bomb. Don't run it. Yo, what's up everyone? My name's Dave, and you suck at programming. Except today, you suck at using the terminal, and I'm going to show you how to get better, okay? Now, a lot of you have been asking me a couple questions. You asked me questions on my previous videos, like, how did you jump around the words like that in the terminal? And how did you just swap two words like that? That's crazy. What are you doing? Well, let's talk about it. So here, I made a handy-dandy guide here. This is not exhaustive. There are way more options than this. But basically, we can, let's say we have echo world hello, something like that. We have a command. We have 3 different words there. First things first, we have Alt F and Alt B, or, you know, Meta F and Meta B, whatever your keyboard has. That will jump forward and back words. So this is how I move my cursor back and forth so quickly. The alternatives are, instead of Alt, I can hold Control, and this just moves 1 forward and 1 back. This is useful because I don't have to move my hand over to the up, down, left, right buttons. Moving your hand over the arrow, very slow. Keeping it on the keyboard, home row, very fast. So what I have here is Alt-T is to translate the 2 words. So if I were to want Alt-T, I have the cursor between world and hello. Alt-T, bam, echo hello world. That looks a lot nicer. There's also Control-T, which will swap the 2 characters. This can get confusing, but still super useful. So Alt will do it on a word level, Control will do it on a character level. There's also Control W, that will just delete back a word. So if I have a bunch of words, I can just Control W, Control W, Control W. Control U, delete everything. Now that is super useful, because have you ever tried to sudo a command and then it asks for your password, you start typing your password, you're like, oh, I made a mistake. Uh-oh, now I got a backspace or hit enter and it's wrong. Control U, retype in your password, bam, super simple, super easy to use. Control R, reverse search, this is super nice. Hit, instead of having to search through your history or press up until you find something, Control R, type in something, and bam, it'll bring up my last echo command. All I typed in for that was echo, and I hit enter to run it. Cool, super useful. Well, there's a little bit more than that. So these shortcuts are Readline shortcuts. Readline is a library that you can use, and it's baked into kind of a lot of programs, or it might be linked against it. Bash uses Readline, but there are other programs that use Readline. A good example would be like a node REPL. You fire up a node REPL, you could say like var foo equals hi, console.log foo, and then if I press up, you can see I'm going back to the history. If I use Alt B and Alt F, I'm jumping around words the same way. Control W will just, bam, start deleting words. That's because they both use readline under the hood, so all of the shortcuts are the same between Bash and Node and other REPLs that use the same thing. The other thing is they have history. You notice how I press up and down and I can go back? Well, each has their own history file. So Bash has, you know, what was it, .bash_history in your home directory. I think Node has like, I'm just going to tab complete it. Yeah, Node REPL history. Same idea. It's just a file in your home directory that holds the history. Cool thing you can do. I don't know why you'd ever want to do this, but you could do this. You could fire up Bash without readline support. So you just do no editing. Bam. So now what do we have? We have Bash running, but I can't control L. I can't press up. I can't press down. There's really not much you can do here. I just realized the prompt's probably cut off. But yeah, if I press up, if I press down, it's no good. This is not useful. I'm gonna press Control D and back out of that shell. Okay, and yeah, so hopefully this gave you some insight into Readline. You can look more up on Readline shortcuts and stuff like that. Get really fast, get really useful. If you're going to be using the terminal every day, especially in a professional setting, you might as well get fast at it. So yeah, hopefully this is helpful. So what's up, everyone? My name is Dave, and you suck at programming. And today, we're going to fork bomb one of my machines. A bunch of you in the comments have been asking for it. I talked about fork bombs before, and a bunch of you were like, why not run it? Just run it. And it's like, all right, you know, you're being a little cringe, but fine. I'll run it for you, all right? All right, so let's get started. We're going to start by SSHing into a different machine. This machine is a VM because I'm not going to run it on a real physical machine, all right? We're going to run this on a virtual machine. So right now we're on a virtual instance of Linux. Nothing special going on. This is void Linux. This is running 2 gigs of RAM. How many processors do we have on this? I think it's just 2 maybe? 4 processors. Okay, 2 gigs of RAM, 4 processors. This is running in hardware virtualization. Nothing special going on here. So yeah, let's do it. All right, do you guys remember how to write the fork bomb? Let's see. Define a function called colon, open it up, colon calls itself, pipes itself to itself, puts itself in the background, and there we go. Now we've defined the function, and the final step is the trigger. We need to actually call the function itself. Here we go. Running a fork bomb. That's it. All right, let's, there we go. This is what you guys wanted to see. ls, nothing, control C, nothing, control D, nothing. I don't know what to do. All right, let's go over to a new terminal, SSH into the machine. It's hanging. This is probably what would happen if you run a fork bomb on your machine. It would just, oh, wait, hold on. I'm lying to you. It's not hanging. Let's see, can I ls? No, I still can't do anything. I was able to get in for a second there, but I'm not able to do anything. I was actually surprised by that. I didn't expect that. So what should we do here? Well, okay, control C can't do it. So let's kill SSH. You guys all remember how to do that, right? Tilde.enter. That's how you kill SSH. All right, so we have a normal prompt here. What can we do? Let's SSH into the hypervisor. This is an OmniOS machine. I'll bring this to the top for you guys. OmniOS machine, so it's running in a zone. We can do a ZADM list. I have a lot going on, don't I? Let's ZADM list specifically void. There we go. We can see 2 gigs of RAM, 4 GPUs. ZADM power off void. We have to reboot it. We don't have a choice. We have to pull the plug on the machine. So over here, you can see it stopped running, nothing's going on. Tilde.enter, bam, okay. SSH isn't running, or sorry, we're not SSH anymore. Can't log in because we pulled the plug. If we list it, we should see that it's installed. Yeah, okay, cool. So what we can do now, we can boot it. Let's reboot the machine. And this is how you would fix it. You guys wanted something awesome and climactic? I'm sorry, it's just a fork bomb. It's super boring. It just exhausts all the resources. You can't log in. If you can barely run anything. The best thing to do is just reboot the machine. Unplug the power, plug it back in. Log back in. Hey, look, we're back up. We can run it uptime. We can see that it was up for 0 minutes. Everything looks good. Hope you learned something. Yo, what's up, everyone? My name's Dave, and you suck at programming. All right, today we're going to go over a fork bomb like we did before. If you have seen my previous episode, I talked about a fork bomb and how it works on a Unix system. Well, today we're going to go through it step by step, very slowly, with safeties in place, so we're not going to crash a machine. We're not going to exhaust all the resources. We're going to do a little mini controlled nuclear test on this machine, okay? All right, let's get started. So what we're going to do here is we have a program called Step Bomb. This is a step-by-step fork bomb. There's a lot going on here. I'll break it down line by line. I'm going to scroll right to this line. There's a function called bomb, and bomb calls itself and pipes it to itself. That is the essence of the fork bomb. You know, colon, pipe, colon, ampersand. This is bomb, pipe, bomb, ampersand. The only difference is our bomb function takes a couple of arguments. It takes 2 arguments, a number and a name. And we use that as identifiers. We're going to print that out. This is just for our benefit. So we started off, we are at number 0, and our name is none. We don't have a name yet. So when we run, we increment the number, so then we'll call bomb with the number 1 and the left side, the number 1 and the right side. We'll be able to keep track how many layers deep are we, that's what the number's for, and if we're on the left side or the right side of the pipe, that's what left and right are for respectively. And then right here, this is our safety, okay? We got the safety on. When number reaches 6, when we've iterated from 0 to 6, we are going to quit the program. When it gets to 6 layers deep, there's a lot of processes running, okay? So this is just arbitrary. I've picked it because it's a good way to show what's going on, all right? And then we print F here. This is a little bit confusing, but what we're printing is just what's gonna be happening. I'll show you. It'll make more sense when I actually run it. There's gonna be a lot of output, but let's go for it. We're gonna run step bomb. It's gonna run up to 6 layers deep, and then it's going to exit. So, step bomb. Bam, okay. As you'll notice, the program finished before stuff was running. A bunch of the output is out of order. You can see there's some 6 and some 5s here. There's a lot going on. Because everything's happening asynchronously, it's being forked in the background, a lot of things are happening out of order. But luckily, because I put the number first, we can sort it. So that output was going to standard error, so it wasn't being piped into anything. So we have to write all standard error to standard out, and then we can sort it, and we will rerun it. Okay, so what do we have here? We have 0, and then 2 1s, and then 4 2s, and then 8 3s, and then 16 4s. Take my word for it, there's 16 there. I'll prove it later. It's growing exponentially. When we get to 5, there's going to be 32. When we get to 6, there's going to be 64, all right? It's growing exponentially. It's pretty gnarly. I can prove this, which is cool. All right, now the prompt's going to get a little bit out of hand, so I'm just going to set a new prompt so I don't overflow the screen, because I know you're probably watching on your phone. And yeah, let's give you some more room. Okay, so we got a nice small prompt. What can we do? Well, we can run step bomb. We can put standard error to standard out, and then we can sort the output like we did before, and let's just get the first field. The first field is the number. This is how many layers deep we are. We got rid of the left and right. We got rid of the word running. We just have the numbers. Why do we have this? Well, we can pipe it to unique-c. This will do a frequency count of how many times they show up. So what happened here? Well, at layer 0, there was 1 running process. At layer 1, there were 2 running processes. On iteration 2, there were 4 running processes. On iteration 3, there were 8. On 4, there were 16. When we got 5 layers deep, there are 32 processes running. When we get 6 layers deep, there's 64. That's crazy. The reason it's crazy is because if we got to 7, we would have 128. If we got to 8, we'd have 256. It's growing exponentially. Each one of those is a process that's going to be running. You're going to exhaust your system of resources if this continues. Luckily, we put that safety in there to stop when it got too high. We can verify that it's exponential growth because all that means is, let's say 2 to the 0, I'm getting the number 0 here, should equal 1. So 2 to the 0, oh no, I shifted it. 2 to the 0 is 1. So 2 to the 1 should be equal to 2. 2 to the 1 is equal to 2. Cool. 2 to the 5 should be equal to 32. 2 to the 5, 2 to the 5, 32. There you go. So 2 to the 6, which was the next one, 64, obviously. And like I said, it would just keep growing exponentially if we were to let it keep going. So yeah, this is why fork bombs are dangerous. They will just keep growing exponentially. Luckily, we had a trigger in there to stop it, but we had all those processes running. We had a lot running. So yeah, hopefully that was useful for some of you. Yo, what's up everyone? My name's Dave and you suck at programming. All right, today we're going to talk about simple IO redirection in Bash. All right, what is IO redirection? Well, let's talk about a really simple command. Echo hi. What did that do? It printed hi to the screen. What if we echo hi and we redirect it to dev null? Didn't print anything. Why? Because of IO redirection. We told it that the echo command, its standard out, should be set to dev null and not to the controlling terminal, so we don't get any of the output. Why is that useful? Well, we can do some magical things. We could redirect this instead of to a file, we could redirect this to an open file descriptor. We could write this to standard error. This still shows up on a terminal, but this is interesting because what if we grep for hi? Well, that should show up, right? I mean, hi's in the output. Grep returned an error though. The word hi showed up, but grep returned an error. Isn't that interesting? What if we grep for foo? Hi still showed up. That clearly doesn't match foo. So what's going on here? Hi is never making it to the grep command because hi is going to standard error. It's being written to the terminal. It is not going through the pipeline. The only thing going through the pipeline is standard out, which in this case is nothing. So that's why grep is failing. Grep's not finding any of those patterns because nothing's making it through. Let's talk about how this can get more complex. I have a simple program for you, and this program is called program. There are 4 echo lines in this program. These 2 are functionally the same. Echo, this goes to standard out. It doesn't have anything at the end of it. This one also goes to standard out, but it redirects to file descriptor 1. File descriptor 1 is standard out on a standard Unix machine. Let's go down here. What happens here? This one goes to standard error. Why? Because we're redirecting it to &2, standard error on a standard Unix machine. What we're doing here is we're going to creating a new file descriptor. We're creating file descriptor 3 and we're duplicating it, so it's going to point to what file descriptor 2 points to. So this also goes to standard error. We wrote it to 3, but it's going to go to standard error. Let's run this program. Is this any useful? Let's see. So we ran the program, we get 4 lines here. We get this goes to standard out, this also goes to standard out, this goes to standard error, this also goes to standard error. So let's pipe grep for this. Hey, that looks right? The word this shows up 4 times and we found it 4 times and grep didn't return an error. The output's a little out of order, standard error showing up first, that's interesting. So what's going on? Well, the same thing as the example before. If we grep for foo, you can see that standard out is filtered out, but standard error is not filtered out. That's because standard error is not going to the grep command. We can change this though. We could redirect everything to, let's say, 2 greater than ampersand 1. This redirects all standard error to standard out. Now we can grep over everything. And as you can see, nothing shows up, which is good because foo is not in the output. This is in the output and it will show up 4 times, which is exactly what we want, and this makes perfect sense. A couple more complex examples you can do with this. You may have seen something like this where someone's like, well, what if I wanted to throw out the standard error and keep the standard out? That's classic. You could just do 2 greater than dev null, and we threw out all the errors and we only kept the output. Some people want to do the opposite. What if you want to keep the standard error but throw out the standard out? Well, okay, let's see. Let's throw out the standard out, and then let's keep the standard error by redirecting it to standard out. So what's going to happen? Well, we threw out everything. That's because the order of operations matter here. We told 1 to go to dev null, which is standard out, and then we told 2 to go wherever 1 is going, which is going to be dev null now. So we have to do it out of order. We have to specify 2 go to where 1 currently points to, and then override 1 to point to dev null, and if we run this, we only get the standard error because we redirected things in the right order. And there you go, that is some Bash IO redirection for you. Yo, what's up everyone? My name's Dave and you suck at programming. All right, today we're gonna talk about running commands over SSH and quoting variables over SSH and how they can get real hairy real fast, and some tricks for how to deal with it so you can stop being cringe losers about it and be base like me and know how to run commands without running into quotation issues with Bash, okay? Let's go. All right, so first things first, let's run a really simple command. We can run the uname command. I'm on my Apple machine, so you can see it says Darwin, that's the name of the kernel. Cool. We can SSH into a different machine and run commands. Did you notice? I can SSH into my void machine and run uname, and I can see that it's running Linux. I can SSH into Arbiter, and I can run uname, and I can see that it's running SunOS. So you can just give a command to the end of the SSH command, and it will run on the remote host and then return back to your local host. You don't have to actually SSH in and create a interactive session. You can just run commands remotely like this. Super, super useful. Let's talk about something else and I'll show you how they relate. Okay, you might have been in a situation like this where you want to echo a variable and print it out. So let's say we want to look at our current working directory. Look at that, we're in users Dave, dev, you suck at programming, part 19. That's our current working directory on this machine. Super cool, right? Well, let's SSH into our void machine and run echo pwd. Now, if we run this, we still get the same directory, even though I can tell you that directory does not exist on that machine. So what's going on? Well, the variable is being expanded on our local side. We're quoting it like this. So you might think, okay, well, let me put this quote here so this whole thing gets processed on the remote end, right? Nope, still being processed on the local end. Okay, maybe you think, oh, I'm smarter than that. I'll put the single quotes here, and then we'll run it. And there you go. That's great, but what's going on here? This whole thing is being passed to a shell on the remote end, and this variable is being expanded unquoted. That's not a problem right now, but what if the present working directory had a space in it, or multiple spaces, or new lines or tabs? I mean, if you're familiar with my channel, you know I love to do crap like that. So this is fine, but you're still expanding this variable without quotations in a shell. It's less than ideal. So let's talk about some ways to fix this, okay? One of the easiest ways to fix this is to think, what am I trying to accomplish? You're trying to get your current working directory. In this example, this is a variable. So what we can do here is instead we can run commands in the remote end. What I'm going to do is I'm going to use hyphens here to separate, so I can say SSH to void and then put some hyphens here, and then I can run the command on the remote end. This just separates the SSH command from the actual local command that I'm going to run. Remote command, I shouldn't say local command. So what can we do here? Well, there's a lot of things we can do here. We could run very simply printf. Printf just prints an environmental variable without having to expand it. So if I just say pwd and run this on the remote end, bam, there we go. There's my present working directory on that machine. I didn't have to use any quotes. I didn't have to use any $ or expansions. Super duper simple. Also, let's not forget that present working directory is a command. You can just run pwd. Bam, there you go. There's the answer to your question. Which pwd is running? That's really interesting. What kind of question is that? Well, if we run type on pwd, we can see that's a shell built in. It's also a command. So which one's running over here? Well, I'll give you a hint. I don't want to actually give you a hint. I'll just show you how to get the answer. It's the shell built in that's being run. This is being executed through a shell. So why is that interesting? Because we could either run the built-in pwd manually, or we could run the command pwd, which I believe on this end is bin pwd. Yeah, there you go. But you don't have to think about this. You don't have to worry about any of this. You can just run pwd and bam, there you go. That's the command you want to run. So, moral of the story is you can quote it. You can find a way to quote it. If you find yourself escaping quotes, you're probably in too deep. Break apart what you're doing into more manageable chunks. Find the right program to execute. Stay away from quotations and expansions if you can. But otherwise, just make sure you quote everything properly. And there you go. There's quotations in Bash. Yo, what's up, everyone? My name's Dave, and you suck at programming. All right, today we are back here with everyone's favorite programming language, Bash. All right, let's jump into it. Today we're talking about arrays in Bash, all right? The reason we're talking about this is because a lot of you guys don't seem to know that there are arrays in Bash. You guys seem to think it's totally acceptable just to have long strings separated by spaces, and that's good enough. And yeah, I guess it'll work for you, but it can break in really fun and sometimes subtle ways. So, let's talk about it. All right, let's look at the cringe script first. This is what you guys think is good. This is what I think is cringe. Look at this. We have a variable called names. It's set to a big string, and as you can see, there are 4 names here: Alice, Bob, Claire, and Dave Eddie. Very simple, A, B, C, D. Awesome, great. Notice that Dave Eddie has a space in it. Uh-oh, is that gonna be a problem? Well, let's see. We do for name in $names, so we expand this variable here. We don't put any quotes around it. We don't do anything. We just expand it as is in the for loop, and then we loop over it, and then we print a little arrow sign and the name. So, what do we get when we run this cringe script? Uh-oh, there were 4 names and we have 5 lines of output. Why is that happening? Well, it got confused. It saw the new lines, it saw the spaces, and it treated both of them as delimiters. So we got 5 names when we wanted 4. So, okay, cool. How do we fix this? Well, the fix is simple. It's how I started the video. We need arrays. So let's look at the based version. All right, you guys ready for this? Base, same exact thing, except this time we have an array. You can tell we have an array because we open parenthesis and we close parenthesis, and then there are 4 strings in here that are quoted, so Bash knows that they're strings: Alice, Bob, Claire, and Dave Eddie. And then we use this funky syntax. If you're familiar with the channel, you've seen me talk about this before. We do the open curly brace, close curly brace here, open square bracket, close square bracket, and then we use the @ sign. The @ sign allows us to iterate over every element of the array. And then we run the base script, and bam, exactly what we wanted. 4 names, 4 lines of output: Alice, Bob, Claire, and Dave Eddie. Cool. So some of you might be wondering, you may have seen this syntax before. I have one last script for you here. This is a very interesting script. Let's take a look at this one. We have a new array called ARR. We open parenthesis, and we have 4 elements in this array: the string foo, the string bar, the string baz tab bat, that's a literal tab character, and then new, and then a literal new line. So we have some funky strings in here. So I'm going to show the difference between using a star as an expansion and an asterisk. Not an asterisk, an @ sign as an expansion. So we have the asterisk up here, and we have the @ sign down here. Other than that, these for loops are exactly the same. We just do for thing in, and we echo cringe, and then we echo base. So let's see what we get when we use a star for an expansion or an @ sign for an expansion. We run it, and here we go. So if we use the star for expansion, we only had 1 element that got iterated over. We printed cringe once, and the entire thing we printed was the array stringified. When you use an asterisk, you will get that as a string. It will join it together. In this case, it joins it based on the inner field separator. So we have 1 line, 1 element. If we use the @ sign, this works correctly. We had 4 elements, we have 4 lines here: foo, bar, baz and bat, and then this, I actually lied, this is a 5th line, but they're all the same element. As you can see, base was only printed once, the arrow was printed once, and then new line down there. So yeah, that's a little, that's something on Bash and arrays. Yo, what's up everyone? My name's Dave, and you suck at programming. All right, today we're gonna talk about something fun. We're gonna talk about quotations and how to escape them in Bash. This is something that trips a lot of people up. If you've ever seen someone use the shell and they really don't know what they're doing, I'm talking about you. You know I'm talking about you. Where something breaks because a quote is not closed or something's open, you don't really know what's going on. You're like, oh, I got single quotes here and I don't know how to escape it. How do I escape a single quote in a single quote? You're probably in too deep. You probably need to step back and reevaluate what you're doing with your life, but we're here, all right, and we're going to figure out how to do it, okay? I'm going to walk you along. You can feel safe now. I'm here. I'm by your side. Let's do this. Let's escape some quotes. All right, so first things first, let's open up our first script we have here. We have 2 variables, single and double. Why are they called that? Because single has single quotes in it, and double has double quotes in it. So as you can see, this string has single quotes in it, and it has double quotes surrounding it. This one has single quotes around it, but it has the double quotes in it. And there's nothing tricky about this. Don't worry, I'm not fooling you, all right? We're going to run this, and it's going to work exactly how you think. The strings get printed No problem. We have single quotes, we have double quotes. As you know, if you use double quotes in Bash, parameters will get expanded and variables will get expanded. If you use single quotes, they will not get expanded, all right? I don't need to harp on that, but it's something to keep in mind, all right? So let's look up a different example. We have both, all right? So we have this string, it's open and closed with double quotes, and inside it we have single and double quotes in it. Hey, that's cool. We use double quotes to actually create the string, and inside we can have double quotes. We just have to escape them. The reason we escape them, we put a backslash in front of them, is to sort of say, hey, we're not closing the string yet. We actually want this literal quotation to be in the string. And again, no trickery here. We run it, and it works. All right, let's move on. We have another script. We have this script called uh-oh. And why is it called uh-oh? Because this has a single quote in it, but as you can see, it's using single quotes to escape it. So will this work? As you can see, the syntax highlighting thinks that this word single is something special. So question, will this work? Well, let's find out. The answer is no. It lost the single quote. It worked in the sense that it printed it, but it lost the single quote. Why? Because we open the string here, we close the string here, but then we just keep putting data here, and then we reopen, and then we close again. But in Bash, as long as they're all next to each other, they'll all get stored as a string. So how do we keep these single quotes in here without changing these surrounding ones to double quotes? What we have to do is we have to put an escaped single quote here, and then we can reopen the string, then we can close the string here, put an escape single quote, and then reopen it. So what do we have here? We have 3 single quotes here. Why do we have 3? Because we have one at the beginning, so we have to close that one at the beginning. Okay, we closed it there. Then in here we put a literal single quote, so this is our way of saying we're not opening another string. And then this one right here, we are opening another string. And then we just do the exact same thing here. So when we run this, we get, look at that, we now have a single quote in it. Awesome, how great is that? That's cool. Kind of weird, but cool. All right, and then what do we have for the last one? Here is a little treat for you guys. This is called a here doc. Now this is super useful. So in this example, I'm using the read command here, and the read command allows me to take data from standard, in this case, from standard input and read it into a variable. So read, I'm using -r, this is raw input, -d, and I set the delimiter to nothing. The reason I do this is because otherwise it would be separating it on new lines, so we get rid of that. We have my var name, that's just the name of the variable that we're saving the data into. And then this is the important part, this is the meat of it right here, all right? We have less than hyphen EOF. That means it's gonna read everything until it sees this exact string of characters, EOF, it sees EOF down here, and bam, now we have this string. It has double quotes in it, it has single quotes in it, we don't have to escape anything. We can even look in variables, we can do variable expansion like user and home, and if we run it, we get, oh, that's not right. If we run it, we get that whole string. Look how awesome that is. And you can see it got the variables, it expanded them exactly how we wanted them to. That is pretty neat. You might be thinking, oh, but I didn't want them to expand. What can I do? Well, you can quote EOF. So you can just put EOF in quotes, and then you can see these stop being syntax highlighted. And then if we run the here doc command again, you'll see that $user and $home were not expanded. Put quotes around EOF if you want to stop expansion. Don't put any quotes and you will get variable expansion. All right, and that is a crash course on escaping quotes in Bash. Yo, what's up everyone? My name's Dave and you suck at programming. All right, today we're going to talk about a really fun subject. We're going to talk about command substitution in Bash. All right, we're going to talk about backticks. You might have seen them. They look like this. And that might be a little bit dangerous to run the shell, but let's do something like this. We can echo, and then we can run echo high, and then we can close it, and it will print high. That's because this echo high is being run, and then the output of that is being substituted as an argument to this echo. A little convoluted, this example's a little contrived, but just showing you the basic gist of it. You might have seen these backticks. I'm gonna show you why they're cringe. All right, let's jump in. So let's look at the first script we have here, cringe. Hello, your kernel is uname. Now, will this run? Of course it'll run. Hello, your kernel is Darwin. Awesome, I'm running it on my Mac, that makes perfect sense. That doesn't seem that cringe, right? And in that specific example, no. There's really nothing cringe about that, but there's a better standard you can use, all right? We're gonna go over here to cringier. Why is this cringier? Well, look what's going on here. We're making a variable called example, and we're storing it to the output of this command, this entire command. We're gonna echo this entire thing. So the variable will be set to echo your name is, and then you can see the who am I command is being run here. This whole thing is being stored as a string called example, and then we print out example. So what happens? It might be easier to show this example just by running it. Your name is Dave. Cool, it ran the who am I command and it got my name. My name is Dave. Awesome. Why is this cringy? Well, we have a backtick here, and then we have nested backticks, so as you see, we have to start escaping them. And if we were to have another nested in there, we'd have to start escaping the backslash, which escaped it, so we'd have 3 backslashes. and it just grows, and it's bad. And oh man, there's a lot of things that can go wrong with that. It can get very confusing. You can have unexpected side effects. We start using backticks. So let's look at a little way to make this cleaner. All right, let's jump into O2, and as you can see, there's two examples here. Your name is who am I, and then down here there's a variable called good, and it's your name is who am I. So what's the difference here? Well, there's a different syntax. We can use the backtick syntax if we want to, but we can also use this syntax. This syntax is where you do a $ open parenthesis, and then anything in there will get executed as a command, and then close parenthesis when you're done. Why is this better? Well, it's really simple. In this example, you can see when you nest it, you don't have to escape anything. We can just open up another one of these here, and it's like a stack. We just stack these on. If you've ever done that, you know, the CS program where you had to write a calculator, that's what we're doing. We just keep pushing these on the stack, and then every time we see a parenthesis here, we pop them off the stack, all right? So we don't have to worry about escaping. There's no trickery. There's no weirdness there. If we run this example, I wrote to the file. If we run this example, you can see your name is Dave. It works exactly how we expected it. And if you're in this situation, if you find yourself in the situation where you're nesting command substitution, take a step back and think, is this really what I want to be doing, okay? So I'm going to show you the based way. The absolute based way is we just throw all of that out, and we just accomplish the same thing. By getting rid of the echo command, we're saving it to a variable. We don't need echo. Echo is redundant. And then what are we doing here? We know that the whoami command, we can just get $all caps user. Bash has this built in. You can look at the man page. You can find all these variables. We run this. Bam, your name is Dave. So much easier, no backticks. So again, the base way to use backticks is don't use backticks at all. Have a good one. Yo, what's up everyone? My name's Dave and you suck at programming. All right, today I'm going to tell you why you suck at using the shell. And what do I mean by that? You're probably confused by your shell. You probably log in and you're like, oh, I don't really know what file's being read. Is it my bash RC? Is it my Z shell RC? Is it my bash profile? Is it etc profile? Where are my environmental variables set? I need to put something in my path and I try to modify my path variable, but it's not there. What the hell is going on? I'm going to answer a bunch of those questions today, all right? So to get started, we're going to log into a machine I have. We're going to log in this machine called Arbiter, and we're going to see what happens. Bam. Okay, so what happens here? We log in, we get a little message of the day, we get a little OS so we can see that we're running OmniOS, and then we get hi from /home/dave.bash_profile. Why do we get that? Well, I'm logged in as Dave, and we are in my home directory, and as you can see, there's a bash profile file here, and inside it just says just echoes hi from here. So it lets me know this was being sourced. So when I log in over SSH and fire up bash, you can see that it reads from a bash profile. What if I fire up bash inside here? What if I just execute bash? Well, now it reads from my bash RC. Isn't that weird? Okay, what if I fire up bash with -l? Well, it reads from my bash profile because that's a login prompt. That's kind of weird. Can we make it more complicated? Of course we can. What if I become root? What if I want a sudo on the machine? Sudo -s. Well, okay. I have root privileges now, but it read it out of home Dave bash RC. What if I sudo -i? Well, I have root privileges and it read it out of /root.profile. Okay, cool. Sudo su root. I want to just become root, pull in all of root's environment. We've pulled in /root.profile. That's kind of interesting. Why do we pull in .profile and not bash profile? Well, let's look. There is no file named bash profile. I'm tab completing and nothing's happening. Let's open it up and make one. What happens if we make one? Hi from root bash profile. Okay, so we have this file now. So we log out now. Let's log back in with sudo. And this time it read it from my bash profile. So isn't that interesting? If bash profile doesn't exist, it reads it from your profile, but if bash profile exists, it reads it from that and doesn't even try to read it from profile. How interesting. There are so many different places this could possibly be read from. Are there rules to this? Does any of it make sense? And the answer is yes, of course there are rules for it. All right, you can pull up the bash man page. You can look for something like bash_profile, and we can get some information. Okay, cool. You can run bash with --no profile to tell it not to read it. But right here you can see by default, bash reads these files when it is invoked as a login shell. See invocation below. So if we look for invocation, we can go down to the invocation section, and here we can see a list of the files that are pulled in, and it tells you it changes based on if --login is present, which is -l like we used before. It'll read from etc profile if that exists. After reading, it will look for bash_profile, bash_login, and profile in that order, reads and executes the commands of the one that exists and is readable. So because bash profile existed, we didn't make it to bash login or profile. There are rhymes and reasons to this, okay? There are reasons that it gets executed in the way that it gets executed, and sometimes it's easy just to be like, I don't know where things go, I'm just going to dump it in every file. Slow down, read the documentation, figure it out, understand it, and then if you so choose, you could have your bash RC just execute what's in your bash profile and you can consolidate it all down to one. That's what I do. My bash profile might actually be a symlink to my bash RC. I don't remember how I have it set up. So yeah, there's some cool information on login shells with bash. Yo, what's up everyone? My name's Dave and you suck at programming. All right, today we're going to talk about port forwarding with SSH. SSH local port forwarding. All right, this is useful when you have a remote machine and you want to connect to some service on that remote machine, but maybe that service is locked down. That service is running on the remote machine, but you have to be on that remote machine to access it. Well, we can port forward from our local machine to that remote machine, then we can access stuff locally. Might be a little confusing. I'll show you what I mean, all right? So here we go. We're on my local machine. This is my Mac. My Mac's name is Studio. And if I curl localhost 8000, you will see that it fails to connect. There is no server running on this local machine, all right? So do I have a server running on 8000? Well, I do. It's on a different machine and it's not accessible from the outside, all right? So let's log in to that other machine. We're gonna open up a different terminal here. We're gonna log into this machine called Arbiter. And then now that we're on Arbiter, we can run localhost 8000 foo.txt. Bam, we can see there's a web server running on this machine called Arbiter and it says hello TikTok. Super cool. Well, how can we access this on this machine? The answer is port forwarding, and we can do it through SSH, so it's secure. How do we do this? Well, we can do SSH-L 8000 localhost 8000. This syntax trips up a lot of people. Keep watching if you want me to break down this syntax, all right? I'm going to demystify it because this is stupidly confusing, and it doesn't have to be. It's actually very simple once you understand it. But we log in with this, we go back to our local machine, we rerun that curl command, and bam, look at that. It acts like it's running on the local machine, even though it's not. This data is being proxied over the SSH connection to Arbiter and then being flown out of Arbiter effectively to go and hit the web server that's running locally, and we can get this information now. So again, back to this syntax. This syntax trips a lot of people up. Here's what I want you to do. I want you to look at this part first. This is the remote machine, okay? This is the machine where the web server is running. It's running on localhost 8000, localhost as seen from the Arbiter machine, okay? This is where the remote stuff is running. This is the local port to open. This is the port on the local end that gets open. So for instance, I could change this to 1234, run it, go over here, change this curl command to grab 1234, and I get the same result. All right, super easy, super simple. In fact, even though I'm logging into Arbiter, there's no reason I have to talk to localhost. There could be a different web server. Maybe I have to jump through Arbiter to get to a different host. Maybe it's on a VPN or something. I can do void. Void is the name of a different machine. Void's not a keyword. Void is the name of a machine, just like Arbiter is the name of a machine. So we're gonna log into Arbiter and we're gonna forward commands locally on port 1234. We're gonna forward requests to void at 8000. So everything stays the same over here. We run this, but we get different output because we're not hitting the web server on Arbiter. We're going through Arbiter to hit the web server on Void, which has a slightly different file for us. All right, so hopefully this demystified local port forwarding for you with SSH. Yo, what's up everyone? My name's Dave and you suck at programming. All right, today we're gonna talk about SSH, specifically SSH keys, the SSH agent, how all that authentication stuff works. And the reason we're doing this is because guys, some of you guys in the comments have been asking, hey, are you SSHing without a password? Do you have no authentication? That's kind of cringe. What are you doing? Of course I'm not, all right? I'm not using a password, but I'm using keys, and I'm gonna show you guys how to set up the exact same thing that I have set up here. All right, so to get started, I'm gonna show you an example. So let's say I'm on my local machine, and I wanna log into a machine I have called Arbiter. I can run SSH, I log right in. Let's say I wanna go through Arbiter, and I wanna get to Void. Okay, works no problem. Doesn't ask me for a password, just uses the keys under the hood. How do I know this? Well, I can run SSH add-L, and I can see that my key is loaded. So I have this key currently loaded, and I can log into other machines using this key. The key is on my desktop and the agent is being loaded. The agent's being forwarded to all these machines so they can talk back over the socket and they can authenticate requests. So none of these machines can see my key, but they can ask something to be, they can answer challenges using this key. So let's back out. Let's back out a second. Let's log back into Arbiter, but this time we're going to run with -A. What does this do? This disables forwarding of the key. So now that I'm logged into Arbiter, that key is not being forwarded. I can run SSH add-L and I can see that there is no agent running. If I try to log into Void, it fails. It gives me permission denied. Cool, I can't go out anywhere here. So why is this important? Why is this useful? Well, I'll show you. So right now I can start my own SSH agent if I wanted to. Typically you would do this in some sort of, shell startup script or something, and you wouldn't do this by hand, but I'm gonna show you how to do it by hand. We can run SSH agent, and now it is running in the background. It forked itself, it's running in the background, and it gave me this stuff. It gave me a link to the SSH auth socket. This is where the socket lives. It showed me the current running PID, and it echoes the agent PID is here. This is meant to be executed by your shell. So I can Command C, Command V, it's a little bit different than Control C. Copy and paste. I can copy and paste it. Bam, I copied that in, I paste that in. So what does that let me do now? If I run ssh add -l and list my keys, you can see I'm getting a different message. I'm still getting an error, but the error isn't that it's not running. The error is that I have no identities. I have no keys. So what can we do? Well, we can create a new key. So let's create a new key on Arbiter. We'll run ssh-keygen, no arguments, and it will ask me where do I want to save this key. It uses the default path of .sh id_rsa. Let's go with that. That's fine. Do we want a passphrase? Sure. How about we'll make the passphrase, you suck. Bam. And there we go. Now it created a key. So what exactly did it create for us? Well, I'll show you. In .ssh, where is it? .ssh is a directory. There is id_rsa.pub and id_rsa. So what are those two files? Well, let's check them out. id_rsa, this is my private key. It is encrypted with the password I used, you suck, but this is the private key. And then what is the .pub? This is the public key. This is what I can give to other people. If you've ever seen a authorized host file or something, like, let's see, I'm on a void machine and I can look at my .ssh and there's authorized keys. This is what you would put in there. Authorized keys, not authorized hosts. This is what you would see in there. If you were on someone's GitHub and you want to look at their public keys, this is what you would see, this format. All right, so what can we do with this? Well, we can give that public key out to people, and then we can log in, or we can give it out to different machines, and we can log in using this private key. Well, first we have to load the key into our agent. We just created the key, but we didn't load it into our agent. We can load it with ssh-add. This will automatically find the key here, and then we can put the passphrase in, you suck, and now we added the identity. So what does that mean? If we run ssh add -l, we can list it, and we can see that this identity is currently running. You can also run it with -L, and you will get the same output. You will see this is the public key. It outputs the public key. So what can I do with this now? Well, we can use this key to SSH into void. If we SSH into void right now, it still fails. That's because void doesn't know about this key. We just created this key. So let's go over to here. I already have a terminal open to void. This is through a different connection that's not using any of those keys. Imagine you logged into this machine manually or through a password or something. We can edit the authorized .ssh authorized keys file. And you can see there's already two keys in here. I have one for my M1 MacBook and one for the Studio. That's just the names of them. That's what I'm reading off of. The names are at the end. And then we can edit this. We can dump the new key in here. We can write and quit the file. And now that new key's in there. So we can go back here, rerun the SSH, and bam, we're logged in using that brand new key that we just created. So yeah, hopefully this helped demystify SSH keys for you a little bit. Yo, what's up everyone? My name's Dave and you suck at programming. All right, today we're going to talk about parameter expansion in Bash. You might be wondering, what's parameter expansion? Well, it's a really cool way of expanding variables and being able to do some manipulation on them. This is typically like string manipulation. This is stuff where you might see someone forking out to sed or awk or tr or cut or any of those commands. You can probably do it all in the shell, and I'm going to show you how to do that. This is a crash course. I'm not going to go in deep. There's a lot to parameter expansion. I'm going to show you just some simple examples that might be useful. All right, let's get started. We have 4 scripts here. Let's look at the first one. First script is super simple. We have a contrived example where we have a file name, and then we just have this set to what a normal file name would look like, /home/foo/bar/baz.txt. It's a made-up file name. This file doesn't exist. The point is we're going to do manipulation on this as if it's a string. First thing we're going to calculate is the base name of the file. The base name of the file, I'll tell you right now, is just baz.txt, and then we're going to calculate the dir name. The dir name is /home/foo/bar. So if we run this script, there we go. We can see that it prints the input. This is the input string. And then we can see that we have the base name here and the dir name here. All right, cool. How did that work? Well, we did parameter expansion. We open up the curly brace here and we close it at the end of the string. What we do here is ##**. It's extraordinarily terse. Doesn't really tell you what it's doing. I'm going to break it down for you. All right, pound means we're going to delete starting from the left of the string. Double pound means we're going to be greedy. We're not going to stop the first time we encounter the pattern we're looking for. We're going to go all the way until the last occurrence of the pattern. The pattern we're looking for is star, anything, and then a slash. So anything up into the slash, into the last slash of the string, we are just getting rid of. So starting from the left of the file name and working our way forward, we see anything up to the slash, but we keep going because there's more slashes. We keep going until the final slash. We delete everything to the left of it and the slash itself. So we are just left with baz.txt. By contrast, what we do to file name is a little bit different. We do a %/*. The percent sign is the opposite of the pound sign. We are starting from the right and working our way to the left. We're starting at the end of the string and working our way to the beginning of the string. We are not being greedy. We only have 1% sign, so we're going to stop at the first occurrence, and we're going to delete everything to the right of the slash that we encounter. Now, this is the first slash, but again, we're starting from the right of the string. So if we go up here and we start from the end, we go all the way to the left until we encounter this slash, and then we delete it. So everything from this slash to the right is deleted, and we're left with slash home, slash foo, slash bar, and that's exactly what we have in the output. All right, let's look at some more of these examples. We have a basic string replace. So we have a string called old. This is kind of a cool string, I guess. Simple enough. And then we have a string called new. We take the string called old, and we do a slash notation. Slash what we're looking for, which is cool in this case, slash what we want to replace it with, Nito. As you can see, Nito doesn't show up in the string, but it will because we're going to replace the word cool with the word Nito. And if we run it, we can see this is kind of a cool string, I guess, and then this is kind of a Nito string, I guess. So pretty cool. You can do basic find and replace with parameter expansion. Let's look at this example. So this one's called unset. The reason it's called unset is because we have two variables here, 1 and 2. 1 is set to hello, and 2 is set to the empty string. It's set, but it's set to the empty string. So what do we do here? Well, we print variable 1 : foo, and then we print variable 2 : bar. So what's going to happen? Well, let's run it. This is the easiest way to see. We print hello and we print bar. Why do we do that? That's because this expansion says print whatever's in 1, and if there's nothing there, print the literal string foo. This one says print whatever's in variable 2, and if there's nothing there, print the literal string bar. So because there was something in hello, instead of printing foo, we print hello. But with 2, there was nothing in 2, so instead of printing nothing, we print bar. So we get hello and bar, which is exactly what we see. Last example, I have some extras in here. This is super simple. Let's say we have a string that just says hello world, capital hello, capital world. We're going to print the input string unmodified, and then we're going to do this expansion, which is comma, and this expansion, which is uptick, I don't know what those things are called. Caret, yeah. So let's run those. 03, we run that, and we can see our input is hello world. The comma is to lowercase, and this is all uppercase. You might have seen TR commands doing this. You can do this in Bash. Be careful. This might not be, I think this is supported in Bash 4 and above, but I'm not sure the versioning. Be careful. Sometimes these parameter expansions can fail if you're on a machine that doesn't have a new enough version of Bash. But this has been around for a while, and it's pretty useful. So yeah, hopefully this enlightened you on parameter expansion in Bash. Yo, what's up everyone? My name's Dave, and you suck at programming. All right, today we're going to talk about signals, specifically signals in Bash and how to deal with them, all right? So let's get started. You probably dealt with signals, and you didn't even know it, all right? So let's say we're on the terminal here, and we're going to run, I don't know, a command that'll take a while, something that'll take too long. Let's say we're going to sleep for 30 seconds. And we're like, you know what? I don't have time for wait for this. This is too much. I don't want to sit here. I don't want to be stuck here. Control C. We're done. What happened? What actually happened when I pressed Control C? Well, that signal was sent to the process. Control C actually gets turned into SIGINT, or interrupt. It's the interrupt signal. And then sleep receives that signal. Sleep doesn't do anything special, so it goes to the default behavior that all processes will go through, where all signals are fatal. So that will just kill it. Bam. Sleep is just going to die. Cool. Not a problem. We can just Control C stuff to stop it. Hey, that's pretty simple. What can we do with this information? Well, let's say we make a script here. And in this script, we trap the SIGINT signal, and we do our own thing. So in Bash, we can do this. We can use the trap keyword. We can tell it what to run, and then we can tell it on what signal we want this to run. So when there's a SIGINT, we want to run the function on SIGINT. And as you can see, the function is defined up here, and all it does is print SIGINT received, ignoring LOL, and it doesn't do anything. It doesn't die. It just keeps going. And then our main program here is just an infinite while loop where we echo the word tick and we sleep for 1 second. So what happens when we run this? Well, we go in that infinite while loop, and it just ticks. It ticks every second. Okay, I'm sick of this. Control C. Uh-oh. Control C. Uh-oh. No matter how often I Control C it, the script is trapping it, and I'm stuck here. So what can I do? I can do something really interesting. Control Z. Control Z will stop it, and now from here, it's put it into my jobs. I can run jobs, and I can see that it's currently stopped. I can run FG and put it in the foreground, or I can run BG and put it in the background. All right, really interesting. So now that it's in this form, I can kill it. I can do %% for like the last background job, I think. And now it's gone. Terminated 15. What does that mean? Well, it sent signal 15, which happens to be sig term. That's another signal. So when we kill a process, by default, we send it sig term. We tell it to terminate. And that's exactly what it did. And hey, that's super cool. What if we don't listen to sig term? What do we do now? Same exact program, but in this time, we trap two signals. We trap SIGINT and SIGTERM, and we just ignore both of them. As you can see, we're going to print slightly different messages, but the idea is the same. So what happens then? Well, we run this. We can't control C it. It doesn't work. We can control Z it, but if I go to kill it, it just prints that it received the signal, lol, and now it's running again in the background. So what do we do? Let's foreground it. Let's run Control Z again, and now we've stopped it again. So we can run jobs and it's still there. Well, this is where we bring out the big guns. We can sig kill it or kill-9. You could use the actual name if you want to, but I'm just gonna do kill-9 %%, and bam, nothing can trap that signal. That is sig kill. It's done. It's not running. If I run jobs, it's no longer there. We don't have to worry about it ever running again. Cool. What about if we were to run this script that I wrote? This is a fun script. We just have a function called onSignal, which just traps signals in general, and we trap SIGINT, SIGTERM, and SIGTstop. SIGTstop is what gets sent when you control Z. When you freeze a process and put it in the background, like with the with terminal with Bash or something, this is SIGTstop. So let's trap that. What happens now? Same deal. I can't control Z it. What if I control Z? Uh-oh. I'm a little bit stuck here. So what do you have to do now? Well, this is where your sysadmin skills have to come into play, because now you have to open a different terminal and you have to find that running process and you have to kill it yourself. From here, we can run PS and we can look for the process that we know is running and is causing us problems. We know the process starts with O2. There's a lot there. How about all LOL? There we go. Two things pop up, the grep and the bash program itself. The bash one is what we want. This is the process that's causing us a problem. We can grab that PID, kill-9, go over here, and then you can see it's dead. It's not running anymore. We almost got stuck, but we were able to navigate our way out of it, and that is how to process signals in Bash. Yo, what's up everyone? My name's Dave and you suck at programming. Alright, today we are talking about checking return codes inside functions in Bash. That's a little weird. I'm going to explain what I'm talking about, alright? So let's take a look. What do we have here? We have 4 programs, okay? We're going to run through 4 programs today. Let's take a look at program 1. Inside program 1, what do we have? Well, we have 2 functions defined. We have the function named good and the function named bad, and all we do in this program is we execute good and then we execute bad. Super simple, super straightforward. Let's look at the good function. What do? We run the command true, and then we echo the return code of true. So you can see here we echo the word good, $$ $? Is the return code of the program that ran before it, of the line before it. So $? Here will be the return code of true. $? Here will be the return code of false. If you're confused, each command in Bash, each line will have a return code. This will signify it was successful or not. So if it's 0, it was successful. If it's anything that's not 0, it was a failure, all right? So let's run this and let's see what we get. Program run. Okay, perfect. Program 1 ran, and we have 2 lines of output. Good, return 0, bad, return 1. Well, that makes perfect sense because good was successful, so it returned 0. Bad was unsuccessful, it ran the command false, and that returned non-zero, or in this case, 1. That's simple, that makes sense. Cool, let's look at program 2. So what's going on here? Let's open that up in Vim. So now you can see we are capturing the output of true and false. So we're running output equals true, and then output equals false. We're doing this $parenthesis notation to actually execute the command. So we're executing the command true, we're executing the command false, and we're storing the output. We're not doing anything with the output, but we're storing it for now. So what happens if we run this? Well, we can see good is 0 and bad is 1. Just like our first program. That makes perfect sense. The exit codes line up with the command that's being run. So the exit code for true is shown and the exit code for false is shown. Awesome. What about program 3? Now, program 3 is pretty cringe. This is something you guys would write, all right? So what do we do here? Well, we have 2 functions, good and bad, and as you can see, it's almost identical to program 2, except we have this local keyword. We're trying to be good. We're inside a function, so we're gonna make a local variable. This variable is not global. It will not exist outside this function. So we make a local variable called output, and we set it equal to the output of the command true. And then down here, we do the same with the command false. What happens if we run it? What was it, program 3? Good returns 0, but bad also returns 0. So what is going on? We know that bad should return 1. Why did it return 0 here? Well, the exit code that we checked right here, we're not checking the exit code of false. we're checking the exit code of the local keyword. The local keyword is telling us if it was successful or not in creating a variable named output and setting it equal to the command false. A bit confusing. If you've never seen this, it seems a bit odd. It is a bit odd, but this is what's happening here. So if you want to turn this cringe script into something base, we can look at program 4. This is where I fixed this issue. Basically, we have to break the local definition and the output of the command onto 2 separate lines. So we have to declare the variable and then initialize the variable here. As long as we do this separately, local will return 0, letting us know that it was successful, and then output, just like in program 2, will tell us if it was successful or not. So if we run program 4, we get good 0, bad 1, and that is what we expect. And that is local return and exit codes in Bash. Yo, what's up everyone? My name's Dave and you suck at programming, and today, we're not even going to talk about programming. Why? Because we never talk about programming on this channel, let's be honest. Today we're going to talk about Bash. Not really. We're going to talk about different utilities and Unix tools you might be used to, like ls, grep, things like that, and how you might be used to the GNU variants without even knowing it. So for example, if you're on a Linux machine, you're probably using GNU variant, a GNU version of ls, grep, all sorts of other tools they have. If you were on, for instance, like my Mac, or you were on an Lumos machine, or you're on a BSD machine, you might be using other versions of those tools. They're still going to work kind of how you expect them to, but there's going to be different options, things that you may or may not be used to, things you may expect to be there, and they just quite aren't working the way you expect them to. So I'm going to give you a quick little demo of that right now. So right now we are on Linux. Cool, simple enough. And we're in a directory called temp files, and there's nothing here. So let's touch some files. Let's make A, B, C. Now if we run ls, there they are. Cool. There's my files. There's 3 files, exactly how we expect. Let's create a 4th file. What are we going to call this file? Well, we're going to be mean. We're going to call it the escape code for red, and then we're going to call it D, because that's the name of the file, and then we're going to exit that escape code, and we're going to reset the terminal back to normal. So what happens? Well, when we ls the file, you can see, look at that. That's a weird file, isn't it? ls-l. Okay, we have one super weird file and 3 other files that look kind of normal. That's kind of neat. That's kind of cool. Why am I bringing that up? Well, let's go over here. We're on a different machine now. We're not in Void anymore. We're on Arbiter. What is Arbiter running? Well, we're on SunOS, okay? So this is an Illumos system. Let's do the same thing. We're in temp files. There's nothing here. Touch A, B, C. Cool. We have 3 files. ls-l. Okay, cool. We have 3 files just like we expect. What if we touch the same file? Tput, set AF 1, so set the foreground color to 1, which is red, D, and then SGR0 to reset it. Bam. Now what happens if we ls? Well, we have 4 files. One of them is D, and it's red. ls-l. Cool. One of them is showing up as red. How fun is that? So notice that ls on the GNU side, on the Linux side, actually escapes it, and on the Illumos side, we don't have that. Doesn't mean that we can't do that. ls is just slightly different, so we might have to say ls-b. There we go, ls-q. One of them will not print control characters, the other one will escape all characters. You have similar options on these variants, I believe. Yeah, same thing. But yeah, just be mindful of this. So if I were to put something like gnarly in here, maybe a character to clear the screen, it looks like ls on Illumos might actually just clear the screen. And you know, it's kind of what I'm asking it to do, but yeah, just something to be careful about, something to be mindful, cool little trick to show your friends. Yeah, that's it. Yo, what's up everyone? My name's Dave and you suck at programming, and today, we're back in Bash, all right? We're not even going to talk about programming, we're talking about Bash. So what we're going to talk about today, we're going to talk about IFS, ifs, the inner field separator. We're going to talk about that variable. We're going to demystify it ever so slightly. I've talked about this in the past. I've showed a couple examples, but this time I'm going to drill in specifically into this variable and give you one quick concrete example that can help you understand it, all right? So let's come up with something really simple. Let's make an array. Cool. How do we do that? Well, we just use parentheses. So A equals foo bar baz. Bam, now we have an array. So what happens if we echo $A? Well, we're in Bash. We only echo the first element of the array. If you were in Z shell, this might be different. I don't actually remember off the top of my head, but in Bash, we only get the first element. So how do we figure out how many elements are in it? Well, first thing we have to do is we have to wrap it in curly braces. This is exactly the same as the line above it. Now that we have it in curly braces, we can use the square bracket notation. So in the square bracket, we can do a whole bunch of stuff. We can put a star here, get every element of the array. We can put an @ here, get every element of the array. If you want to know the difference, I have a video explaining this. But if we want to know the count of it, we can actually put a £sign in front of this, and we can see that there are 3 elements in the array. Cool. Let's talk about IFS. So first thing we can do is we can do what we did above. We can print the variable with the star notation. The star notation stringifies it, okay? And this stringifies it using the IFS. So right now the IFS is set to the default value, which is a space tab new line in that order, and it's grabbing the first character from it. It's a list of characters, grabbing the first one, and it's separating them by that. So you can see it's separating them by spaces. What if we unset IFS and then we run it? Cool, we get kind of the default behavior. What if we set IFS to the empty string? So it's set to nothing. What happens now? Look at that. So we stringified it, but we used what the IFS was set to. It was set to nothing, so it joined the elements of the array by nothing. So they are squished up on each other. What if we were to set the IFS to colon? And then we were to do it. Bam! Now we have colon separated values. How cool is that? What if we were to set the IFS to, I don't know, underscore A, B, C, D, E, F, G, something like that. Underscores. It only uses the first character of the IFS. So that is a quick, cool little way of dealing with the IFS and Bash and joining variables and arrays and all that crap. Cool. Yo, what's up everyone? My name's Dave and you suck at programming. All right, today we're back in Bash and we're going to talk about globbing. What exactly is globbing? Globbing is, you've probably seen it before, you've seen the star operator. You ever see someone do, ls and then the ls star? That star expands to all of the files that are in your current directory. So if I were to echo star, you can see it shows me the exact same thing that ls does. Star is a glob. So we're going to talk about that. Why is that important? Well, let's consider this example. So we have here a directory called files, and inside files, there's nothing in it. It's an empty directory. All right, pretty simple, right? So let's look at the cringe script. Let's say we wanted to write a script to loop over all the files in a directory, print out the name of the file, and then show how many files there were. So if there are 5 files, we would print 5 lines with the name of the file, and then we would print the number 5. Cool, simple enough. Let's look at the cringe script. This is what you guys think is good. This is what you guys in the comments are telling me how I'm gonna do it, all right? Cool, so let's take a look at this. What do we have here? I equals 0. We initialize a variable called I equal to 0 at the top of the loop. Then we do for f and file star. Cool, so we're looping over every file that's in the directory called files. We know there's nothing there, but the script doesn't. We're gonna print file colon and then the name of the file that we find, and then we're gonna increment the variable I. So then at the end of the loop, we can say found $i files. So if we found 5 files, we should print 5. If we found 0, it should say found 0 files. Cool, let's run your cringe script and see what happens. Uh-oh, what happened here? Cool, we printed out 1 line, so it looks like it found 1 file. What file did it find? It found files/star. That's kind of odd, isn't it? And it says it found 1 file. Like, how dumb is that? What happened here? Well, the glob failed. There was nothing to glob inside file. So when the glob fails, it doesn't get expanded into all the files because there was nothing there to expand to. So it stays as a literal file/star character. So we can see right here, it actually tried to look at a file with this name and it failed. That is normal Bash behavior, all right? So if you want to protect against this and you want to prepare yourself for this, there's one little line you can add. So let's look at the base script right here. This is your magic little line right here. Shopt-s nullglob. Shopt will allow you to turn on shell options. This is specifically for Bash, so we can turn on the nullglob option. The nullglob is pretty simple. All it says is if a glob fails, it gets expanded into nothing. So what happens if we run it now? Well, let's go ahead and run it. Base script, run it. As we can see, we printed 0 files were found because there are 0 files there. So that is how to use nullglob in Bash. Yo, what's up everyone? My name's Dave and you suck at programming. And today, we're going to talk about pgrep and pkill, some super useful utilities you can use on the command line instead of having to do this garbage where you guys are in the comments, you're talking about, oh yeah, I do ps minus ef, pipe for grep my program, and then I grep-v grep. Get the hell out of here with that stuff, all right? We're talking about pkill, we're talking about pgrep. Your life's about to change for the better, all right? So let's jump in. What are we doing with? What do we got here? Well, cool. We actually have a C program. Not Bash. That's not Bash. Can you believe it? We actually have a real programming language. Oh my god, let's talk about this. So what does this program do? I wrote this program specifically for you guys to illustrate this concept. So what does it do? Simplest program in the world. We just pause. All this program does is it starts and it pauses. It hangs. It doesn't execute. It's equivalent to sleeping forever. That's all it does. Technically speaking, it actually pauses until a signal is received, but we'll deal with that later. So that's all this program does. So if we run it, it just hangs. Cool. Awesome. So what can we do? Well, let's run it, but let's put it in the background. We use an ampersand, put it in the background. And we know, because we're on the shell, its PID is 68342. But let's say you were running a script or you had this already running on a machine and you wanted to find it. And you, let's say, no output. We don't know what it is. Uh-oh, what is that? I have no idea. Well, how would we find it? Well, we know the name of the program is my program, so maybe we'll do this cringe thing you guys have been talking about. Let's grep for my program. What do we have? Well, we have 2 results. We have this, And then we have the actual grep itself, because remember, grep is a program that's running at the time that PS is running. They both get executed at the same time. This is technically a race condition. The fact that we see this, we're lucky. It's possible that we may not actually see this. So what do? Well, a lot of people just say you do this. You grep-v grep. We filter out grep. Cool, now grep is gone. We're just left with my program. We know the PID's here, so how do we grab that? Well, we can maybe pipe it to awk, and we could grab the second field, just like a nice sysadmin, and there we go. We have our PID. That sucks. Come on, guys. It's 2023. Grow up. pgrep, my program. Done. There it is. There's your PID. You want more information about it? pgrep-l. There you go. It actually gives you the PID, and it gives you the program name with all the arguments. They would appear over here. That's how you use pgrep. It's super simple. And then if you wanted to, I don't know, maybe kill it, you could do pgrep, and then you could pipe it to xargs kill. Even that's overkill, right? Look at this. pkill, my program. This will kill every instance of a program named my program. Be very careful with this. If you were to type something like pkill Firefox, goodbye browser. But let's pkill my program, bam, terminated. It's gone. Now if we were to pgrep for it, nothing shows up. If we were to do that atrocious psef, nothing shows up. Bam, there you go. That's how to use pkill and pgrep. Yo, what's up? My name's Dave and you suck at programming. All right, today we're gonna talk about the prompt in Bash, specifically the PS1 variable and the PS2 and other variants, all right? We're not talking about the PlayStation 1. God, I wish we were. Parappa the Rapper. It's just a fantastic game. There's no game that even comes close. But we're gonna talk about the prompt in Bash and how to mess with it. So actually, I'm gonna start by breaking the fourth wall. When you watch my videos, you might see a little prompt like this, where it's just simply a $sign and a space, and then I can type in things, and that's all well and good. That's not what my normal prompt looks like. My normal prompt looks like this, but that's a lot to put on TikTok or whatever social media platform you're watching this on. But there's a lot of stuff going on here. It has my name, it has the host name of the machine I'm on, it has the uname output, it actually has the directory that I'm currently in, it has the git branch. There's a whole bunch of crap going on here, right? And that's a lot. So when I'm giving one of these demos, I like to say PS1 equals, and then I just put the prompt here that I want as a string. Bam, there we go. That's how I do it. So you can do some customization with this. This is actually kind of cool. So instead of saying like I just put a $sign here, I could actually escape this $sign. It will look exactly the same, but this will be a £sign if I was running as root or with escalated privileges. I can do some other stuff. I can put a \u here, I can put a \d here, an s, a w. There's a whole bunch of stuff going on. Check it out. U will get translated in my username. D will get translated into the date. S will get translated into the shell. W gets translated into, what is this, the base name of the working directory, I believe. There's all sorts of stuff you can do. You could even just put like a whole bunch of like, I don't know, this. You can make it all fancy, and then your prompt looks like this. And yeah, you can go wild with it. So what else can we do? Oh, there's a PS2 variable. You might not even know this exists. When would you ever see the PS2 variable? First, let's reset the PS1 variable. PS2 variable shows up when you're using a here doc. What's a here doc? Well, a here doc is this. See that less than hyphen EOF? Now cat is waiting on input. Here is my input. Control D, no, EOF. There we go. Here is my input. As you can see, look at this. The greater than, that is your PS2 variable. So if I were to say PS2 equals, hi Dave. There we go. And now we're to rerun that command. That's a bad example. Let's rewrite it from scratch. Cool, it says hi Dave. Hi. Hello. You suck at programming. EOF. Cool. So this prompt is the PS2. The prompt you see here is the PS1. There are other ones. I think like PS4 is used for trace logging or like set xtrace, something like that. I don't even remember specifically offhand. There's a whole bunch of magic variables. You can find them if you do, I believe it's like help bash or something like that, or just help man bash. I don't know. They're somewhere in the documents. I have a little notes thing right here. You can peruse this at your leisure. I'll vim it so it's easier to see. There's a whole bunch of examples. I lifted this from the internet. Whole bunch of different examples you can use for different expansions in your prompt. But yeah, that's some demystification around PS1 and PS2 prompts in Bash. Yo, what's up everyone? My name's Dave and you suck at programming. All right, today we're gonna talk about some magic that happens. When does the magic happen? Well, the magic happens when you take ls and you pipe it to word count. If you're in a script and you want to figure out how many files are in a certain directory, don't do this. There are better ways to figure out that information, okay? Don't pipe ls, don't even parse ls at all. But if you're running interactively and you want a real quick synopsis, you're like, how many files in this directory? ls pipe word count -l usually works pretty well. I'll show you an example. If I ls, I have a directory called files. I ls that, and I can see there's like things there, I don't know, maybe word count -l, 4. Look at that. A, B, C, D, if I pipe it to word count -l, there are 4 files there. Super simple, super obvious. Here's the problem. Why is it 4? If I ls files, A, B, C, D all show up on the same line, but word count -l counts the number of lines. So if they're all on the same line, this should print 1. This shouldn't print 4. So what is happening? Is ls doing some trickery? The answer is yes. ls is. ls is determining if the output is a terminal and then changing its output based on that. What am I talking about? Well, if we ls files, we get that. If we ls files and we pipe it to cat, remember cat just reads in from standard in and writes to standard out, we get something different. We get the same 4 files, but they are separated by new lines this time. Isn't that weird? A lot of programs do stuff like this and you're not even aware of it. ls is probably the most obvious example. Curl does this. If you have a curl running, okay, cool. It just prints out what it's downloading. But if you were to, I don't know, pipe it to sometimes you notice like a progress bar starts and you're like, you've never seen that before. And that can get kind of annoying. Yeah, a lot of this is because it will determine if the output terminal is an actual terminal or not. Now, how does it do this? Well, it uses a C standard library call called isatty, and we can do that in Bash. We can actually say -t1, 1 is the number for standard out, and we can print something like echo is a tty or echo is not a tty. So you can see that -t1 was true. It would print it is a tty. If we were to wrap this whole thing in parentheses, we would still get the same thing. It just executed in a subshell. If we were to take this subshell output and pipe it to cat, we can see that now we get different output. Because we've been piped to cat, standard out for that area of the pipe chain is not actually being sent to a controlling tty. So we have is not a tty. So can we use this in our own scripts? Well, of course we can. If we wanted to recreate the behavior of ls, we totally could. I have an example script right here. I won't spend too much time on it, but as you can see, we load a list of the file names from the file/star. So everything that's in files, we load that into an array, and then we check. If standard out is a terminal, then we want to separate them by spaces, just like ls does, and then print 1 new line at the end. Otherwise, if it's not a terminal, say we're piping it somewhere, then we want to separate it by new lines. Every single element of the array should be separated by new lines. So then if we run the example, you can see, okay, it was a terminal, so it printed all 4 on the same line. And then if we pipe that to cat, it actually separated them based on new lines. And that's how to check is a tty in Bash. Yo, what's up everyone? My name's Dave and you suck at programming. All right, today we're going to talk about zombie processes. What are they? How do they happen? How can we make them? And more importantly, how can we make them go away? For some reason, zombie processes are really mystical to people. When people see them, they're like, oh my God, there's zombies in the machine. Like, what are we going to do? Oh my God. Shut up, first of all. Okay, calm down. And let's realize that it's not a problem in and of itself. It's indicative of a bigger problem, but the zombie processes themselves are red herring. They're almost never the problem. When you see a zombie process, you want to go to the parent, all right? A zombie process is not something to be worried about in and of itself, but it is indicative of a bigger problem. And I'm going to illustrate how they work and how to actually create one. We're going to create one today. It's going to be a lot of fun. All right, so let's look. Let's see what we got here. All right, we have a really simple C program. Look at that, not Bash. It's C. Let's look at make zombie. We're going to talk about how to make a zombie process. Well, the first thing the C program does is it forks itself. So this takes one process and turns it into 2. As you can see, we're good. We do our error checking. Fork shouldn't really ever fail, so we should never really hit this if statement. So let's talk about the if statement that matters right here. Fork is one of the only syscalls that enters once and returns twice. We now have 2 new processes, a parent and a child. The way to determine if we are the parent or we are the child is the exit code of the fork syscall. So in this case, if the exit code is greater than 0, we are the parent. Why are we the parent? Because we got back the process ID of our newly created child. If we are the child down here, then we can just do whatever we want. We don't have to worry about the parent. So what does this program do? Well, it's really, really simple. If we're the child, we just die. That's all we do. So we forked ourselves, the child dies immediately. The parent is still alive. Now what a good parent should do is when it forks child processes, it should call wait. on the child processes. It should be looking for signals. There's a sig child. It can get a signal from the operating system when one of the children has died, and then it can go actually wait on one of those PIDs or wait on all PIDs, and it can properly wait on the child. What does wait do? Wait signals to the operating system that it's done. It reaps it. It gets the exit code. It causes all the final cleanup to be done. And it most importantly, I guess, frees the process ID up, so now that process ID can be reused by other processes. So what do we do as the parent? In our program, we print creating zombie with PID. So we actually just print this out. This is just for our own benefit. And then we go into an infinite while loop where we do nothing. We ignore any sort of like signals from the operating system. So we ignore sig child. We ignore everything besides for like the kill signals. So we are a negligent parent. We just pause while the child dies. So what happens if we run it? Well, let's run make zombie and fork it into the background. Cool. So now we have the PID of the parent, and we have the PID of the child. So what can we do now? Well, we actually have our prompt back because we backgrounded the process. So from here, we can look to see if we have any zombie processes. Just grep for defunct, and sure enough, we have one zombie process. How crazy is that? Well, we have the parent PID, so what can we do? We can do pstree minus p. That is not what I meant to copy. There we go. Let's actually call pstree on the child. So what do we have here? Okay, we have, this is our init process, we're on Mac. We have the terminal running, the actual terminal server, our login for Dave. And then we have bash, which ran make zombie, which ran the child process, which is now defunct. So it is the zombie. Now, if you look at this, you might think, oh my God, there's a zombie process. Let me copy the PID. Let me try and kill it. Oh my God, why isn't it dying? Oh my God, I know, I'll do kill-9. This has to work. You idiot. It's already dead. You can't kill it anymore. When you have a zombie process, it is a rotting corpse. And who do you look at for this rotting corpse? You have to look at the parent, because the parent is being negligent here. The child died under the parent's watch, and the parent did nothing about it. This analogy is getting away from me. But that's what happened here. So we don't care about the child process anymore. It's gone. This does not exist. We just have the accounting information for it left. The parent is the problem. Make zombie is the problem. So if we were to kill make zombie, we can see it's dead now. Our terminal lets us know that it's dead. We can now look for that, what was it, PS tree, and nothing shows up. We can PSEP for, what was it, defunct? Nothing shows up. The grep shows up, but that's it. There are no more zombie processes. So when you have a zombie process, the zombie process isn't the problem. It's the parent that is the problem. That's the thing you need to deal with. So hopefully that illustrated zombie process for you. Hopefully you guys are less confused after this video. Yo, what's up everyone? My name's Dave and you suck at programming. And today we're going to be talking about Bash. Of course. What are we going to be talking about? We're going to be talking about functions in Bash, all right? You ever seen a function in Bash? It's really simple. It looks like this. We have a function called foo, and it echoes hello $1, so the first argument that's given to the foo function, and then we call foo with the name Alice. Awesome. Why are we talking about functions? Well, look, I mean, very simple, right? That program works the way we expect it to. Did you know in Bash that you can change the curly brace to a parenthesis? Well, what happens here? Why would I even want to do that? If we run it, we get the same output. Cool, so that doesn't really help us. So let's look at another example and figure out why this might be useful. Let's look at our second script. The second script has a variable here, name equals Alice, and then we have a foo function where we set name equal to the first argument of this function, and then we print 1:name. But then down here we call foo with Bob, not Alice, and then we echo what $name is here. So we have $name up here, $name in here. We have the variable here, but then we also have the variable defined in the function. So what's going to happen when we run this? Well, simple. We're going to overwrite that variable. That variable at the top, this name equals Alice, this gets overwritten down here because it's a global variable and we didn't specify the local keyword. So it just gets completely overwritten. However, what if we put parentheses here? Now what happens? Well, let's run that second script again. Bam, we get Bob and Alice. So what does this do? The parentheses cause the function to run in a subshell. This is a different context. All the variables are copied into the subshell. The variables get modified in the subshell, but then when the function is done, all those modifications go away. So the variable name equals Alice is copied into here. Name is overwritten to be Bob. We print 1:Bob, and then when we drop out, Bob is gone, and we're just back with Alice. That's why we see Bob first and Alice second. Cool. So why is this useful though? Because instead of doing that, we could have just done normal curlies like we're used to, and we could have just put a local keyword here and we would have gotten the same output, right? Yeah, exactly. So why is this useful? I'll show you one cool trick with this. You ready for this one? Let's look at the third and final script. We have foo, We use the local keyword here. Cool, we're being good. We echo something, and then we exit. This function dies. So what happens here? Well, we have an echo before function, we run our function, and then we echo after function. Well, what happens if we die in it? Well, we echo before function, we print hello Alice, but then we never actually get the after function thing to print. This line doesn't get executed because we exit. However, if we change this to parentheses, guess what happens? We die, but we die in the subshell. This dies, but then we actually still go. Our script keeps running. That's super useful. That's a reason you might want to run a function in a subshell like this. You can emulate this behavior if you have curly braces here. Say you're using a function that you don't have control over. I can just wrap this in a subshell. I can call that inside a subshell, and that will also stop it from dying. So that is parentheses versus... Yo, what's up everyone? My name's Dave and you suck at programming. Today, we're going to talk about running commands over SSH. It seems kind of simple, right? Why are we talking about it? Well, there are some fantastic ways that it can break, and there are some things that you should be aware about if you're doing this. Say you have a script that logs into a machine remotely and wants to run some commands. This will be of use for you, all right? So pay attention. Let's go. I have a remote machine I can log into, void. And on this machine, I can run something like, let's say, hostname. Cool, it runs the command, it gives me the output, it gives it right back to me, I can do whatever I want with it. That's super neat. Well, on that machine, I have a script for us to use. It's in bin, and the script is called args. This script is really simple. I'm not going to go into detail how the source works, but basically it shows or it echoes back the arguments you run it with. So if we were to run this command, you would see called with 0 arguments. Cool, I gave it 0 arguments. Well, let's give it some arguments. 1, 2, 3. Cool, called with 3 arguments. 1, 2, 3. Hey, it looks pretty good, right? What about if I did something like, I don't know, hello world, but then I made it a string, so it was just 1 argument. Uh-oh, it broke. It thinks it's 2, but I gave it 1. What if I put a bunch of spaces? It loses those spaces. That kind of sucks. What if maybe, I don't know, do I put the whole thing in string? Like, what do I do here? Uh-oh, same thing. Let's back up. What's happening here? Well, this whole command, when you're passing it to SSH, is being ran through a shell. sh-c is being run on it, and it's interpreting this whole thing as one big string. There are some ways you can work around this. I could put double quotes here. And this is great until your data gets funky. What if your data has quotes in it and it's a variable expansion on the local end that's being sent to the remote end? This could break in some really, really fantastic ways. So the thing to be aware of here is if you're passing data up to the remote end and the data might be a little bit more complex than just some CLI flags, you're going to want a different mechanism. Maybe you SCP up a configuration file or something, or maybe you pass it over standard in. So I'm going to show you how to do that right now. Let's rework what we're doing. Let's say our data looks like hello, space, world. Well, we can pipe that to SSH void, and we could read that on the remote end. So we can use cat. Cat reads from standard in and writes the standard out. Cool. Hey, works how we expect it to do. But we want to run bin args, right? We want them to be sent as arguments, but we're getting 0 arguments there. So what do? Well, this is where xargs comes into play. We can do xargs. There's a GNU extension for delimiter, so we can delimit on new lines. And we could run this, and what happens? Called with 1 args. Hello, world. Hey, that looks pretty good. What if we were to make this standard in a little bit fancier? What if we were to say, hello world, new line, foo, space, bar. What happens now? Hey, that's pretty cool. Look at that. It actually correctly identifies it as 2 arguments. So there are some ways to work around this, but at this point you maybe don't want to pass this as arguments. You want to rework your script to maybe read this data and format it however you want it. If you're in control of a script on a local end, try SCPing it to the remote end and just running it there. These are definitely some things to be aware of when running SSH on your local machine. Yo, what's up everyone? My name's Dave and you suck at programming, and today we're going to talk about some garbage I've seen you guys do, alright? In your bash scripts, I've seen you guys do some straight up garbage, alright? Let's take a look at the first script and see what I'm talking about. You want to read a file. Let's say we have data.txt. So I see you guys do stuff like this. For thing in cat data.txt, and then you echo thing. All right, fine. Maybe that looks good. What's inside data.txt, just so we have an idea? Okay, it's a text file. 3 lines. The first line is, yo, what's up, everyone? The second line is, my name's Dave. Third line is, and you suck at programming. Awesome. Pretty apt for this channel, all right? Let's run that first example. What do we get? Well, that sucks. You're supposed to read it line by line, but you've read it token by token. That's kind of garbage, but you know how to use Google, and you know how to use Stack Overflow. So what did you do? You learned about the IFS, right? The field separator. So what have you done? Oh, you've set it. You've set it to a new line, and now you've done your thing. And does it work? Yeah, it totally does work. I wouldn't say that there's anything wrong with this approach. That's a lie. There's definitely something wrong with this approach. It can be done so much better, okay? Don't do this. Don't mess with your IFS. It can have other unintended side effects. There's no reason to do that. You have while and you have read. You have everything you need to do this correct. Why is this a problem? Well, here's something we don't even talk about. This has to read all of the data in before it can start processing it. So let's say instead of catting the data, cat's pretty simple. What if we had a different program called slowcat? Slowcat works just like cat, except that it's slow. This is more like a different command you would run, like maybe you weren't running cat, maybe you were running something from a remote machine, or you were curling something, and it could take a while. Maybe your network's slow, maybe your file system's slow. So slowcat mimics that. So what's the problem with it? Well, let's look at our third example here. What if we use slowcat instead? What's the problem? The problem is that we have to buffer the whole thing into memory. So that took 3 seconds to run. We had to buffer that entire thing into memory before we could even start processing it. That is lame. So what can we do about this? Well, we can use, like I mentioned earlier, a while read line. So this is using fastcat, or just cat, and we're just using a while read line. So we can read the data here, we can process it, and it's super easy and it works and it's great. The nice thing is if we were to rewrite that to, instead of calling cat, call slowcat, let's take a look at what happens. When we run it, it processes it line by line in real time. It doesn't have to load it all in the memory, it doesn't have to buffer it first. It can stream that data. That is super useful. What's the problem with the approach? Well, we lose the exit code. That's the main problem. So in this example, what we do is we read the whole thing into memory here. We save the exit code of slowcat. Then we can process it line by line using this substitution right here. We can read in actual string data and read it as a standard in. And then we can actually get the exit code of slowcat. So the only way to get the exit code is to buffer all the data. Why is that? Well, because when you're streaming data, you don't have an exit code yet. If a command is streaming data in real time, it hasn't exited. So we don't know what the code is yet. It could stream 20 lines and then fail. It could stream 20 lines and succeed. If we want to deal with all those 20 lines as they come in real time, we don't know the exit code yet. If you need to know the exit code and you want to stream the data, reach for something other than Bash. You're not going to be able to do it here unless you come up with some really, really crazy trickery. So yeah, that's why while is better than for in Bash. Yo, what's up everyone? My name's Dave and you suck at programming. Today, we're going to talk about environmental variables because a lot of you guys in the comments have been asking me about them. There seems to be a lot of confusion around them. So we're going to kind of try and demystify them today, okay? So let's get started. Let's talk about Bash, how we can deal with environmental variables. Well, in Bash, how can we differentiate a regular variable from an environmental variable? We really can't. They kind of occupy the same namespace. So if we have foo here and we set it equal to hello, well, we can echo foo. That's really great. That works perfectly. If I start up a new instance of Bash and then we echo foo, it's gone. It's gone because it only existed in that shell. So if we were to echo it now because I quit out of it, hey, foo is back. Well, what can we do? We can export foo. Now it says that it is in our environment. So if I were to rerun Bash, cool. If I echo foo, bam. Now we actually have it. It is set to hello, whereas before we just printed nothing. If we set foo equal to goodbye, and then we echo foo, sorry, this prompt is gnarly. It's set to goodbye. But if we quit out of that shell, and then we echo foo again, it's set to hello. That's because the goodbye was run in a different process and that doesn't persist in the parent process that we're in. So it's back to what we set it to. The nice thing is because we exported it, we can change it here. We could change it to goodbye. We could start a new shell and then we could echo foo and it's set to goodbye. Because we only have to export it once, whatever we set it to now will be set in our environment and will be inherited by child processes. So what are some other fun things we can do with this? Well, here's something interesting. If we use the env command, we can look at my environment. Get ready for this. It's going to be a lot, okay? It's going to show me every environmental variable, and some of them have color in it, and there's a lot of stuff going on. So let's make this easier to look at. Well, we know we set something called foo, so we can grep for foo. There it is. Foo is set to goodbye. Foo equals hello. Grep for foo, and there it is. So the environment is not necessarily a variable that's defined in Bash, but variables that are defined in Bash may be in the environment, okay? So if you have an environmental variable, it will be defined in Bash and you can use it, but just because you have a variable doesn't mean it's in your environment. When you export something, it puts it in your environment, and that will get inherited by child processes or subshells that are created, okay? If you don't export it, it will not be in child processes. It will be in subshells, but it won't be in child processes that get executed. Because env, in this example, env is actually, let's take a look, it is user bin env. It's a command. It's a child process. So we set foo in Bash. We grep for it here. We're actually executing a child process named env, and there it is. It's being sent to the child process. It's being inherited by it. So hopefully it's demystified environmental variables a little bit for you. Yo, what's up everyone? My name's Dave and you suck at programming. And today we're going to talk about a neat little thing that Bash has for reading files, all right? It's called mapfile. Mapfile is super useful. If you want to learn more about it, you can use the help built-in. You can run help mapfile, and this gives you a little man page style output that shows you information about this built-in command. But if you don't feel like reading, because reading's for losers, I'll show you some examples on how to use it, all right? So let's take a look at what we got here, all right? Let's look at our first script, while read. What does this do? Well, this takes data from data.txt and reads it into an array. So this is not using mapfile. This is how you would do this iteratively, okay? So we create a new array here, it's empty. We read data.txt line by line, and then we push each line into the array. And then when we're done, we print the array. We put a less than and greater than sign in front of the line so we can kind of differentiate them better. But let's take a look, all right? So what do we have? We have data.txt. So this is 3 lines, where the first line is, yo, what's up, everyone? Then my name's Dave, and you suck at programming. All right, pretty simple. So then if we run the iterative example, what do we get? Well, we get exactly what we thought. We get the data in the array, we get the less than and greater than in front of it, and it works, and we have loaded up an array. The problem was, look how many lines it took to load up that array, all right? There's faster ways, and that's what mapfile is for. So let's look at the mapfile example. So in this one, let's actually vim it. Bam. Really simple. We run mapfile, then the name of the variable we want to store it into, so we're just calling it array, as you can see, because we're going to print it out here. And we just read in from data.txt. Super simple. So what happens when we run that? Well, it works. The problem is it leaves the new line on there. So if you're used to Perl, you might chomp it or whatever, or if you're other languages, you might trim it or something. Well, we have that too here. So we can do mapfile trim. Mapfile has -t. Really simple. This just trims it. So this script will put a -t on it, and then when we rerun it, hey, look, that's exactly what we want. There are some other cool things you can do. So in this one, there is a -n, and this is a limit. So this will say, at most, read 2 things from this file, which is a nice way of limiting. Say you have a file that might have, thousands of records. You don't want to read all those into memory. You can run this, and look, we only get the first 2 lines, so we've limited to the first 2. And the final thing I want to show you is really cool, is you can specify a callback function. This is wild. So mapfile, we trim it, -C for the name of the function, and -c for how many lines have to be read until we call the callback. I set it to 1, meaning we'll get a callback for every single line that is read, and then we save it to foo and we print out foo down here. So this function will run for every line that mapfile encounters, and if we run it, it will look like that. So as you can see, we sort of have this diagnostic information. We can add some logging or do whatever we wanted to, or process the data that way, and then we have the final array here, which is super useful. So yeah, that's mapfile in Bash. Yo, what's up, everyone? My name's Dave, and you suck at programming. And this time, we're back talking about environmental variables. Why? Well, because a lot of guys had questions when it comes to it, and there's some Linux-specific stuff I wanted to cover, because that's where it seems a lot of the questions were. So right now, we are logged into a Linux machine. This is important because the Linux machine has the proc file system we can use. So as you know, there's an env command, and this shows you your current environment. As you can see, got a lot of stuff going on here. A lot of stuff in my environment. Well, why does it matter that we're on Linux? Well, we can cat proc $$ expands to our current PID, environ. Now what do we get? We get our environmental variables, but they're separated by null bytes, so we're not actually printing those. So what we have to do is we have to rerun that, and then we replace the null bytes with new lines. This will just make it easier for us to read. We run this, and there you go. There's our environment. Some more people are wondering, why is this different? Why is what's in environ for my current process different than what the env command says? And that's because this file is populated at process start. This is the environment when your process was exec, but it's not your environment after it's been modified. So this is a snapshot of what the process looked like when it first started. Everything else you saw in the env command, that was from my bash RC, that was from me manually setting it. I could do export foo equals Dave, and then I could run the env command and grep for foo, and there it is. But if I run the cat thing and then I grep for foo, it won't be there because it wasn't set. This is a snapshot of what it is when you execute the, or when your bash shell, when your shell was executed. So the question came up though, this one was interesting, what about proc self? Because proc has a little helper for you, it's /proc/self, and that always points to yourself. This is nice because in your scripts, you don't need to actually hard code in a PID, you don't need to put your own PID there, you don't need to call get PID, you can just use proc self and let the kernel resolve it for you. So what happens when I do this? Now we have it. Isn't that odd? If we do $, it's not there, but if we do proc self environ, we have it. In fact, if we do proc self environ and look at all of it, we have the exact same output of env. What is going on? Why is that different? Well, here's the interesting part. So as you can see from these two things, it's a little bit different than you expect. This is a snapshot of what $$ looked like when it started. And this is a snapshot of what self looked like, and self is just a string. and that string got passed to cat. So self points to what cat's environment looks like when it was run. So the cat process is a subshell of our shell, so it inherits our environment at that time. So cat's environment has foo set in it, but $, our current bash PID, does not have does not have foo set in it. So that explains the discrepancy. So hopefully that demystified a little bit for you. Yo, what's up everyone? My name's Dave and you suck at programming, all right? And today, I'm gonna do something you guys have been asking me to do for a while, all right? I'm going to look at a bad command and I'm going to clean it up in real time so you can watch my process for how I clean up bash scripts, okay? This is not anyone's command specifically, but this is a conglomeration of stuff I've seen that has resulted in just a wild, gnarly looking command, all right? All you guys out there for some reason love Docker. You guys are like, yo, Docker's awesome. And looking at Docker, I've seen some stuff that is way worse than what I'm showing you, okay? But for some reason, Docker commands love to be just super long and super hard to read, and there's so many things that are quoted, and there's like escape quotes and multiple quoting, and it's just a nightmare, guys, all right? So let's look at the script and let's see what we got going on here, okay? So we make data. So as you can see, we're making JSON data where the name is the first argument and the comment's the second argument. Let's not even talk about the fact that if we pass in a name that has quotes in it, it's gonna break. All right, there's so many things already that I'm seeing all this, but I have to push it aside because we want to clean this up, okay? So we do sudo docker run, blah, 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 all this stuff. We're running a container, we're running bash with -c that runs curl. We're putting that data to localhost 8000. Okay, so we're taking data, we're taking information from arguments, a name and a comment. We're formatting that as JSON, and then we're putting it onto a remote HTTP server. Seems simple enough. Let me show you how I would fix this in real time, okay? So what I would do here is there's a lot going on here. I'd probably break it with a backslash here, and then I would just break it down here. So we'd have the name of the machine down there, and then we can put the command here, and then what gets run in this command could go on its own line. So right here, we already have, okay, we have our Docker command, we have the Docker options up here, the name of the Docker image, the command we're gonna run, and then the specific bash stuff, all right? So we've already broken it down. It's a lot easier to understand what's going on. Let's go a little bit further. Bash-c, we don't need this. This is just extra information. We don't need bash. This whole thing is already gonna get processed by a shell. So we can get rid of this, get rid of the quote here, get rid of the quote here, and then we just have to deal with this weird quoting. Get rid of that, get rid of that. And this already looks so much nicer. We're running a Docker command, we're running it, and then we're just running curl. All right, so let's see if this works. We called it, what was it? WTF. Name is Dave, comment is hello. We run it. And you can see valid JSON is true and we got our information back. So what the server does, the server reads the information that I send it, shows you exactly what information it got, and then it sends it back to you with this metadata letting you know if it was valid or invalid. This is super useful because what if I were to say, I don't know, hello, this has quotes in it. What happens now? Uh-oh. We have invalid JSON. See, the server just told us that what we sent to it was invalid JSON. We have an unexpected token queue and JSON cool. And what we sent it was this. As you can see, it didn't do anything to try and escape those quotes. Not great. So what can we do to make this even better? Well, I'm not gonna do this one in real time because I'd actually look up some of this information to figure out how to do this. But manually crafting JSON and trying to escape it yourself, don't bother. Use a tool that is right for the job, okay? And the tool in this example is I used JQ. So with JQ, you can give it null input, basically saying don't read from standard in. We can give it two arguments, a name, which is set to $name that we've taken as, $1 above, comment, and then we just print the object. And then we put that entire object through this Docker container. So as you can see, there's really no weird quoting. There's no escaping of quotes. So when we run our base script, let's say Dave, hello, we get back Dave and hello. Awesome. Hello, this has quotes in it. Well, look at that. This has quotes in it. And if we go over here, it's being correctly escaped. So can this do all the escaping that we expect it to? Well, let's take a look. What if instead of quotes we had, I don't know, let's put something wild in there. What do you think? Let's do tput set af1 red. We're actually going to put some escape codes in there to make the output red, and then we'll reset it because we're good. So what happens if we run this? Wow, look, it correctly escaped it for us. It's still valid JSON. That's awesome. Using JQ, we can process that. We could say, oh, let's get data comment. Cool, as you can see, it's escaped. So what if I do -r for raw? It's red. it print red output. How cool is that? All right. Use the right tools for the job. Okay. Get rid of all that weird quoting. Break things down into multiple lines so they're easier to read. Don't try to handcraft JSON. Use a tool that's built for that. Okay. Either the programming language you're in will have some facility, or use the JQ tool. I really like the JQ tool. So yeah, that is a sort of real time how I approach some of these gnarly one-liners you guys have. Yo, what's up, everyone? My name's Dave, and you suck at programming. And today we're going to talk about environmental variables in other languages, okay? I know a bunch of you guys are sick of hearing about Bash, so we're going to talk about some other languages. What other languages? Well, let's find out. We have a C file, and we have a Rust file. Cool, we're diving into other languages. How awesome is that? Well, so what can we do? Well, let's compile them, make sure they're actually ready to go. Awesome, so now we have our two executable tools, and then we also have the built-in env command. So we have env here, and if we run this, it gets our entire environment. There's a lot of stuff here. That sucks. If we run our cnv program, we get all the same information. And if we run our rustenv program, we get all the same information. And just to prove it to you guys, I know you guys might be interested, people in the comments will be asking, let's take a look at some of these real quick. cnv.c is very simple. All we have to do is define a pointer to character pointers called environ. As long as that is global, we will have that when we compile on a POSIX machine. So now we just loop through this and we just print what we see. All we have to do is just print this entire string, and that string is key equals value. So we just print those separated by new lines. Very simple. Our Rust program, even simpler. Our Rust program just is for key and value. We enumerate on Env Vars. So this returns an iterator, which returns a tuple of the key and the value. So then we just print this equals that. So key equals value. Very, very simple programs. These are super useful because now we can do something like export Dave foo equals hi, export foo equals by, and then from there we can do env grep foo, and hey, look. Both of our variables are there, exactly like we expect. We could run the C one, grep foo, they're all there. We could run the Rust one, grep foo, they're all there. How awesome is that? That is a great way to grab environmental variables in your programming languages. Other languages will have other facilities. These are just two quick examples. So what can we do with this? Well, the env command is actually more powerful than you guys might realize. With env, I can reset the environment. I can get rid of all environmental variables. So if I run it with a hyphen and then the name of the program here, there's nothing. There was nothing in the environment. I completely cleared it out. I could even run env again. This command admittedly looks weird. Env is calling itself. There's nothing there. Why would I do this? Because I can set things here. Foo equals hi, bar equals by, and then I could run env. There you go. I could run cnv. I could run rustenv. This is a useful way of clearing out your environment or manually setting your environment to only have the keys and things you want in it. And it just goes to show that in other languages, yeah, there's different ways of grabbing the environmental variables, but they all operate largely the same way, and they're super useful. So yeah, hopefully that demystified environmental variables. Yo, what's up, everyone? My name's Dave, and you suck at programming. And today, we're going to talk about how to debug Bash, okay? You're writing a Bash script, something doesn't work quite right, something's a little bit broken, you want to know how. Here's a cool little trick to help you debug this, all right? So let's look at the script, let's see what we have. We have a fun little script here called funscript. And I'm going to give you a little preview. It's broken, okay? I'm not going to tell you how, but it's broken. So let's take a look at funscript, all right? We can see we have a variable here, want user equals Dave, and then we check if $all caps user is equal to want user, then we print, hooray, it's Dave. Otherwise we print, literally, who even are you? So all caps $user, this is the user that's currently logged in. We can verify this by running all caps $user with echo, and bam, it's Dave. So this script should print something like, hey, it's Dave, or hooray, it's Dave. We run it and we get, literally, who even are you? That's weird, doesn't work the way we expected. Well, we can look through the source code if we want to. We could sit here and try and find the bug ourselves, which is pretty easy, it's a small source code. But what we can do, we can run bash -x, and then we can give it the name of the script, run it, and we can see everything it did. So everything with this little plus sign here, this is what Bash did. So the first thing it did is it created a variable called wantUser, and it set it equal to Dave. Cool, that makes sense. Then it checked, this is our if statement, if Dave equals empty string. So Dave is not equal to empty string, so we went to the else block where it printed literally who even are you. So why did that happen? Why is it the empty string? Well, let's take a look at our fun script. As we can see here, this was set to Dave, but this was the empty string. Can you see why? Well, here we go. There's a typo here. Look at this. We defined want user, USER, and this one is USR. So let's put an E here. As you can see, it got highlighted because it matches. These two are the same. Let's get rid of that highlight. So now let's rerun this script, and it should work, and there you go, it works. We can run it with -x, and we can see that, hey, want user equals Dave, if Dave equal Dave, echo hooray, it's Dave, and we got hooray, it's Dave. So there you go. Hooray, it's Dave. Yo, what's up, everyone? My name's Dave, and you suck at programming. And today, we're going to talk about substrings in Bash. Did you know this is actually built into Bash? In your shell, you can do this? Well, let's take a look. We have 4 scripts here, okay? We're going to start with the first one, 00, start from. So what's going on in this script? Well, we have a variable called message. We set it equal to hello world, and then we echo a couple things, message :0, message :1, message :2, etc. So what's that going to do? Well, let's take a look. If we run it, we get that. So let's look at our source code, let's look at the output, and we can see that this is a substring starting from character 0, so it's the entire string. This is a substring starting from character 1, so it just chops off the first character, chops off the second character, third character, etc. You can do colon, number, and that will be a substring starting from that character going indefinitely to the right. Well, what else do we have? Let's take a look. We have start from limit, so that is script is 01. This is very much the same thing, but as you can see, there's a :5 at the end. This is new. So what does this :5 do? Well, this might actually be easier to just see it. So there you go. It prints the whole string starting from the beginning, but only prints the first 5 characters. So not the whole string, the first 5 characters. So now we start from the first character, or the second character, and we can see there's a space there, start from the third character. So this starts from whatever character we told to, but only ever prints 5. So as you can see, we started from character 0, 1, 2, 3, 4, 5, and we only ever print 5 characters. Hey, that's kind of neat. What else can we do? Well, let's look at end. What you can do is you can specify a negative number, and this will cause it to read from the right to the left. So if we run this script, what's going to happen? It doesn't work. The script's broken. Why is the script broken? Well, there's something really interesting going on, and this might be something you've encountered if you started to learn parameter expansion in Bash. This doesn't interpret it as a -0, -1, -2. This is actually the :- syntax. So this says print the variable message, and if the variable message is unset or the empty string, print 0. Otherwise print 1, otherwise print 2. But because message is set, we just print message, 6 times? Yeah, so if we just run it, it just prints like this. An example of that would be like, let's say, foo equals hi. We can echo foo : by, and it will print hi. That's because we set foo. But if we unset foo, and then we rerun that, we can see it prints by. So it doesn't interpret it as a number, it just says : So how do we fix this? Well, real simple. Let's look at the last example. We have the exact same thing. We just put a space there. That's it. So the : syntax is broken up. We have a colon, space, -0, -1, -2, -3. So what happens when we run this? It's gonna be a little bit weird, but bear with me here. You can see the first one where we specified -0. Well, that's the same as +0. It's just 0. So this is the entire string. It's a substring starting from the beginning. But then -1 would be the last character, the last 2 characters, the last 3 characters, the last 4 characters, etc. This might be common syntax you've seen in other programming languages. And there you go. There's substrings in Bash. Yo, what's up, everyone? My name's Dave, and you suck at programming. And today, we're going to talk about why sudo echo doesn't work the way you expect it to work. All right, we've all been there before. We've all had a file that maybe we need root access to modify, and we try to write to it, and it fails. And then we're like, oh, we should just do sudo, and then we sudo it, and it fails again, right? Here, I'll show you a very concrete example of this. Let's say we want to look at our hostname on a machine. So we cat etc hostname, and that file doesn't exist. Something's wrong with this machine. What are we going to do? Well, we can write to that file. So how do we do it? Well, let's say my host name, and we could write that into etc hostname. What's going to happen if I run this? Well, it fails. We get permission denied. Why do we get permission denied? I don't have access to write to that. I'm not the root user. So how do you solve this? Well, because you're bad and you're cringe, what you think is the right thing to do is you put sudo in front of it. So we sudo it, and we still get permission denied. That's so weird. We're root. Why are we being denied? Well, that's because echo ran with the escalated privileges. This redirect happened in our shell. Our shell was the one that tried to open up that file, and our shell was the one that failed with permission denied e-access. So how do we fix this? Well, you might have seen something to fix this, and they use the T command. So let's explain this. Echo my host name. Let's sudo T that into, etc hostname? There we go. And we'll run this, and what happens? Well, it asks for a password. Okay, cool. Put one in. And there we go. So it printed my hostname, but then it also wrote the file out. So there we go. That's awesome. So what happened? How did that work? Why did that work? Well, let's explain it. There's actually 2 commands running here. There's the echo and the sudo command. Echo runs as the Dave user. Sudo runs as the Dave user, but sudo escalates the privileges. So now T runs as the root user. T is running with escalated privileges. And what T does is it writes whatever it gets on standard in to standard out plus any number of files you specify on the command line. So when I run this, you could have technically ran it like this. It won't print anything, but it will still write it out to that file. So for instance, if I were to like change this to like my hostname 2, and then we recat that file. There you go, we have my host name 2. So it's important to think what is actually escalating privileges. The redirect is happening in the shell, so I would need to either escalate my shell, maybe I could do something like sudo -s, and then I could run as root, and there you go. Or I could just sudo t it, and bam, there you go. So yeah, that's why sudo t works the way it does. Yo, what's up everyone? My name's Dave and you suck at programming, alright? And today we're gonna talk about the alternate screen on your terminal. What is that? Do you not even know? Alright, buckle up, this is gonna be fun. You ever been on your terminal and you're just kind of doing some work? Maybe you're saying, echo hi, or you run ls, and then you say echo, how are you? Just really basic stuff. And then you're like, you know what? I want to look at a word list. Here we go. Here's a list of words. I'm going to run that through less, so I can go up, I can go down, blah, 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 blah. I can page up, I can page down, I can search for something like Dave, and there we go, cadaver. That's awesome. And now I'm done here. So I'm going to quit out. Q. Where did that list of words go? Like, I ran the less command, I did something interactively, but like, where did it go? The answer is the alternate screen, all right? We can get there ourselves. We could run a command, we could just print something to the screen that brings us to the alternate screen. We can use tput, sm, cup, and bam, there we go. Now we're in the alternate screen. Like, hello, yay, we're in the alternate screen. What can we do? We can go back, rm, cup. There we go, we're back. Just like less, we went into this alternate reality, and then we came out of the alternate reality. Isn't that kind of neat? And take a look at this. We can kind of recreate less if we wanted to. This is just sort of to illustrate the concept. We can put ourselves in there. We can get, let's say, the first 10 words from that, user shared dict words. Let's sleep for like 3 seconds just to illustrate it, and then let's rm that cup. Rm cup. There we go. So there we go. We got our words, and they're gone. So yeah, as you can see, this is a simple way of getting to the alternate screen. You would typically do this in a program. Maybe you'd have some sort of library like ncurses or something, or some sort of console drawing program if you were going to do this yourself. But the alternate screen is great. You can go in there, you can do something. Editors typically work out of this, and then when you go back to the main screen, all of that's gone. So yeah, that's alternate screens demystified. Yo, what's up everyone? My name's Dave and you suck at programming. All right, today we're going to talk about programs in Bash, and if they fail during a pipeline, what we can do about it, how we can find out about it, how we can deal with it. Here we go. So let's take a look at this. Let's say we have a really simple pipeline of commands. We echo hi, we do something like pipe it to cat, and we'll say read a file called foo and standard in, and then we'll, I don't know, pipe it to head. Here we go, 3 different commands. We have echo, we have cat, and we have head. We run it, what do we get? We get an error from cat, and then it also prints the word hi, and then we echo $, and we can see that it returns successfully. It's kind of weird, isn't it? We see an error in there, but we return successfully. Now we can see the errors from cat because cat prints itself, but if we had a more complex pipeline, or if we were in a script, what can we do about this? How can we detect this error? Why would we want to move forward even though something broke? Well, it turns out there's a really cool variable for us to use, and it's called pipe status. So let's rerun this command, and now we have this array we can access. So we can look at pipe status. We'll do star, which will print every item from the array. And if we run this, what do we get? We get 0, 1, 0. So there were 3 commands, echo, cat, head, 0, 1, 0. Echo returned 0, cat returned 1, head returned 0. So as we can see right here, there's our problem. Cat was the one that failed us here. This is super useful. This is something you can check if you're writing a program. Say you have a pipeline of like 5 different commands, but you only care if maybe the first one fails or the last one fails. You get the last one for free. That'll be $, but anything else in the pipeline will fail. There are things you can set. There's options like pipe fail and stuff, but maybe you're okay with one thing failing. Maybe you have 7 things in a pipeline and you're like, you know what? Programs number 2 and 4 can fail, but I really want to check program number 3. This is where pipe status is useful. It's super useful. Say you have something crazy. It's just a contrived example. You wouldn't really have something like this. Please don't write a program like this. But you could have something like gnarly like this, and look, it exits successfully, but then if I run this, you can see true exited 0, and then 1 maps up to false here. 0, true, true, and then false up here. So it maps, it makes sense. These are the exit codes. And in fact, they're so much the exit codes, you could manually check this yourself if you didn't believe me. You could say like exit 4, pipe 2, exit 5. I'm putting these in subshells so they won't actually exit my current shell. And let's put an exit 0 here so it exits cleanly. So as you can see, we ran this command, nothing seemed to happen. We run this, and we can see the return codes, 4, 5, 100, and 0. So this is the pipe status variable, super useful, definitely useful in scripts. Not so much in interactive use, but I definitely use this in scripts. So there you go, there's pipe status in Bash. Yo, what's up everyone? My name's Dave and you suck at programming. All right, today we're talking about Bash again. Of course we are, we always do on this channel. Today we're gonna talk about special characters and strings, all right? What am I talking about? Well, let's look at this. Let's say we're gonna run echo, hello, new line, world. What's gonna happen when I run this? We're not going to get a new line. We're going to get a literal backslash and a literal n. So how can we fix this? Well, with echo, we can say -e, which will tell it to expand special characters. So now you can see it shows up on a new line. That's great, but what if we wanted to store this in a string? What if we wanted to say something like s equals hello new line world, and then we want to echo that, but have the new line actually in the string and not just stored as a \n? Well, we can use this syntax in Bash. Put a $sign in front of it. That's it. $, you got your quotes around it, and now anything in here will get expanded. So we can do this, we can echo $s, and there we go. We get our new line. Isn't that pretty cool? We can do some fun stuff with this. So now that we have this, we could do something like, what else? What are some other fun characters? Tab. You know what? Let's just not even save this to a variable. Let's just echo this as is. Echo this with a tab in it, and we get, bam, there you go. There's a tab character. What are some other fun ones? Vertical tab. This one's fun. You guys know about this? /v. So you can see hello's here, and then world is on a new line, but also tabbed to where hello was. This is kind of cool. I don't really know what you do with it, but kind of neat. We can also do \b, I think, for a backspace. So what's going to happen here is we have hell world. I didn't intend that. So hello is 5 characters. So let's backspace 5 characters. And now this should just print world. It actually printed hello backspace world, but the backspaces overrode it. So yeah, this is how you do special characters in strings in Bash. Yo, what's up everyone? My name's Dave and you suck at programming. Today, we're going to talk about background jobs in Bash, okay? Now, a lot of you might know this. You might know that you can run a command on the shell and you can put an ampersand at the end of it, and then it runs in the background. But a lot of you guys don't know what to do from there. There's a whole built-in facility in Bash and a lot of other shells to work with background jobs. So here, I'll show you. The easiest way to teach this is through example. So we can run the jobs command. There are all my background jobs. As you can see, I don't have any. So let's create one. We can do sleep 20, and we can run this, and you can see it hangs. So we'll Control-C that. We'll run sleep 20 with an ampersand. Now what do we get here? We can see we have 1 in brackets and then 4111. So what does this mean? This 1 is the job number. That is built into Bash, and 41111, this is the PID. This is the system process ID. So if we run the jobs command, we can see there's one job. It has an ID, a job ID of 1, and sleep 20 with an ampersand. So in 20 seconds, what will happen is this will finish, the job will finish, and there won't be anything we have to do. So that's pretty cool. So as you can see, it's done now. It's done. Job ID 1 is done. We can run jobs. There's nothing there. Awesome. So why is this useful? Why does this get fun? Well, let's run it again. Sleep 20 with an ampersand. We can run jobs. And we can kill this if we want to. We can send a signal to it. Let's just send the term signal so it stops. How do we send a signal to it? Well, we can use the PID, but the easier way is to use %1. If you use a %sign, it means job ID. So now you can see it was terminated with signal 15. Signal 15 would be sig term. So that's super cool. Kill knows how to send it to Bash. Now you might be asking yourself, how? Why does kill know how to do that? Isn't that kind of weird? Well, let's take a look. Type -a kill. Why does it know how to do that? Because kill is a shell built in. That's why. It's built into the shell, the kill command. Not bin kill. Bin kill is an actual program, and it won't know how to talk to your shell because it's running within the context of a shell. So I can illustrate that. We can do sleep 20 with an ampersand. We can run this. And now if we were to do bin kill %1, that fails. Illegal process ID %1. It does not know how to do it. We could kill the process ID ourselves for 1114. And there you go. As you can see, you can kill it that way. But you can't kill it through job specifiers, which would be %1 in this case. You can also put functions in the background. This is super useful. So if you're writing a script, let's say we have like, I don't know, myfunc, and let's just say this does a sleep 20 and then echoes done or something. So we can have very compound stuff in there. Obviously we can run myfunc like this and it will hang the terminal, or we could run myfunc with the ampersand. We could run jobs and you can see myfunc is running. This would be something you would do in a script, or maybe you had a function in your Bash RC or something that you would use interactively. And then from here, just like before, we can kill it. We can also use %%. This will expand to the last job that's been backgrounded. So this is kind of useful. As you can see, there's nothing here. So we could do, let's say, one last example. Let's run myfunc, myfunc, myfunc. There we go. So now we'll have 3 running in the background. If we were to kill %%, and then we were to run jobs again, you can see 1 is still running, 2 is still running, 3 has been terminated. That's good. %% just means the last thing that was put into the background. And there you go. That's basic job control in Bash.